Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight our journey begins with something both haunting and beautiful. The strange stillness that happens when you follow Einstein's mathematics all the way to the edge of a black hole. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each of us resting under our own patch of sky, yet sharing this same small moment together. Now feel free to dim the lights. Maybe let the faint hum of your room become the background rhythm of your thoughts. And let's gently begin our journey into gravity, time, and the curious places where equations begin to dream. And if your mind starts to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine for a moment that you have an old rival, a friendly nemesis perhaps, and for reasons too complicated to explain, you've placed them in a shining silver rocket and sent them drifting toward the heart of a black hole. You stand far away, safe, your telescope fixed on the ship as it glides through the dark. At first, everything looks ordinary. The rocket moves steadily. Your nemesis shakes a triumphant fist at you once every second, like a clock keeping perfect time. But as the ship drifts closer to the black hole, something begins to change. The rhythm slows. The fist that waved once each second now moves more slowly, as if the air around it has thickened. The light from the rocket shifts, turning redder and dimmer like embers cooling in the dark. And then, at a certain distance, a boundary known as the event horizon, everything seems to stop. Your rival, the ship, the glow of its engines, all of it appears frozen in place. Time, from your point of view, has stopped flowing for them. This illusion is one of the most quietly astonishing predictions of Einstein's general theory of relativity. It tells us that gravity doesn't just pull on things, it pulls on time itself. The stronger the gravity, the slower time moves. Near a black hole, gravity is so intense that time stretches until it nearly stops, at least for anyone watching from afar. What looks like a frozen moment is really the edge of time itself. The light you see from that ship, even as it seems to linger at the horizon, is still travelling toward you. But each wave of light takes longer to arrive than the one before. Its colour slides deeper and deeper into red until it slips past what your eyes can see. To you, the ship fades not because it vanished, but because its light has grown too tired, too stretched to be visible anymore. It's as though the universe itself has decided to whisper instead of speak. If you could somehow see every wavelength, all the stretched out light from every object that ever fell into that black hole, you would in theory see everything frozen on its horizon. The final shine of the star that collapsed to form it, the dust and gas that followed, the ghosts of everything that ever crossed its threshold. But in practice, light is not a continuous song. It comes in tiny notes, discrete packets called photons. There will always be a last photon sent just before the horizon swallows the rest. And so, even this ghostly image eventually fades. For the one falling into the black hole, however, the story feels completely different. Inside the rocket, the clocks tick normally. The heartbeat still beats. The engines hum the same steady note. You wouldn't notice the horizon as you cross it. Space would seem calm. The universe outside would stretch and distort, but your own moment would feel ordinary. This is the quiet paradox at the heart of general relativity. Time depends on where you are and how you move. There is no single universal clock, no cosmic rhythm that beats the same everywhere. Time is local, personal, shaped by gravity's gentle hand. Einstein's equations describe this not as a force, but as geometry. They tell us that matter bends space and time, and that the bending of space and time tells matter how to move. The stronger the mass, the steeper the curve. Imagine a soft rubber sheet with a marble placed at its centre. The marble's weight makes a gentle dip. Now, if you roll a smaller marble nearby, it spirals inward, not because an invisible thread pulls it, but because the sheet itself curves the path beneath it. In the same way, the black hole doesn't tug your rocket in with some mysterious pull. It simply curves space so deeply that every possible path points inward. The event horizon is the point where that curve becomes so steep that not even light, the fastest thing there is, can climb out. If we could translate Einstein's symbols into plain language, they would say something like this. The closer you fall toward a black hole, the slower your time flows compared to mine, and when you reach the horizon, my forever is still your single heartbeat. It's not a wall or a surface, but a kind of invisible boundary in the story of time, a place where the meaning of later changes forever. There's a strange comfort in this too. From far away, nothing ever seems to cross that line. It only fades and slows, becoming part of the still, dark image painted across the horizon. But from inside, the journey continues. The rocket falls, time flows, and space itself seems to draw you onward, as though the universe were exhaling inward. Both views are true, yet they cannot meet. Each belongs to its own observer, each wrapped in its own version of reality. Einstein once said that time and space are modes by which we think, not conditions in which we live. Near a black hole, that idea becomes visible, a living paradox of perception. For you, the distant observer, your nemesis will never quite fall in. For them, there is no stopping, no pause, no sense of being frozen in someone else's gaze. Both are right. The universe, patient as always, allows both stories to be true. And as we hold this thought of two truths coexisting at the edge of time, our quiet exploration begins to drift a little deeper. The path now carries us toward the question that first kept Newton awake centuries ago. How can distant things reach across the emptiness to pull on one another at all? And why did Einstein think that gravity might be something far stranger than a force? If we follow the thread a little further, our story leads us back through time, long before Einstein, long before the word relativity ever existed, to a man who changed the way we understood the heavens, yet could not escape a quiet unease about his own discovery. His name was Isaac Newton. Newton was a genius of rare precision, a man who could see the hidden clockwork of the universe turning in perfect rhythm. He watched apples fall, planets glide across the sky, and tides rise and retreat with the pull of the moon, and he realized that all of these motions were bound by a single rule. He called it universal gravitation. Every object with mass attracts every other object, no matter how far apart they are. The same invisible hand that pulls an apple to the ground keeps the moon tethered to the earth, and the earth bound to the sun. It was a breathtaking idea, a simple equation that could describe the motions of the entire cosmos. But even as he wrote it down, Newton felt an uneasiness that never left him. He could calculate how gravity worked, but not why. In a letter to a friend, he confessed that the notion of one body acting upon another at a distance through a vacuum, without the mediation of anything else, seemed to him so great an absurdity that no man who has a competent faculty of thinking could ever fall into it. He had built the clock, but he couldn't see the gears. What invisible thread connected the stars to the earth? What was this mysterious influence that reached across emptiness? For more than 2 centuries, that question lingered unanswered. Scientists used Newton's equations because they worked so well, predicting eclipses, tides, and planetary motion with astonishing accuracy. But they did so with a kind of philosophical shrug. Gravity was a useful mystery. It could be measured, but not understood. Then, in the early 1900s, a quiet man working at a patent office in Bern, Switzerland, began to wonder if the problem lay not with gravity, but with time itself. Albert Einstein was not content to accept action at a distance. He imagined what it would feel like to ride alongside a beam of light, to live in a world where time and space could stretch and twist depending on how you moved. He started with what he called special relativity, the idea that the laws of physics are the same for anyone moving at a constant speed. In that world, there's no universal now. Two events that seem simultaneous to one observer might happen at different times for another, depending on how fast they're moving. Even before he turned his thoughts to gravity, Einstein had already reshaped time into something flexible, personal, and relative. But he wasn't finished. He began to ask himself, if motion can affect time, could gravity, that most mysterious of all influences, do the same? What if gravity wasn't a force reaching across space, but a kind of bending of space itself? Einstein later said that his key insight came while daydreaming. He imagined a man falling off a roof. As the man falls, he feels weightless. The objects around him seem to hover beside him, falling at the same rate. For that instant, he feels no gravity at all. To Einstein, this was the clue. Gravity and acceleration are two sides of the same coin. Falling freely under gravity feels the same as floating in space. That was his happiest thought. From that single idea, he built something extraordinary, a new way of seeing the universe. He called it the general theory of relativity. In this vision, space and time were not separate backdrops upon which things happened. They were woven together into a single fabric, spacetime, that could bend, stretch, and ripple. Matter tells space-time how to curve. Curved space-time tells matter how to move. It's a sentence that sounds simple, almost poetic, but within it lies an entire universe of mathematics. The relationship between matter and geometry can be written in a compact form that looks almost friendly on paper. But behind that simplicity hides a family of interlinked equations, vast, interdependent, describing how energy, momentum, and mass shape every fold and dip in the four-dimensional fabric of reality. If you could translate those symbols into words soft enough for the ear, they would say, "Show me where matter lives, and I will tell you how space and time must bend around it. Show me how space and time bend, and I will tell you how matter must move." This is what Einstein meant when he said that geometry had become the language of gravity. In Newton's world, gravity was a tug between distant objects. In Einstein's world, it was the landscape they lived in, a landscape that changes shape depending on what inhabits it. You can picture it gently like this. Imagine a great invisible sheet, stretched tight, a fabric that represents space-time itself. Place a heavy ball on it. The sheet dips, forming a shallow valley. Roll a smaller marble across the surface, and it will curve around the dip, circling the heavy ball not because something is pulling on it, but because the surface it travels on has changed shape. That's what happens with the Earth and the Sun. The Sun doesn't pull the Earth with a mysterious hand. It simply bends the space-time around it, and the Earth, moving forward through that curve, follows the path of least resistance, what we call an orbit. In the same way, the Moon orbits Earth, and you remain pressed to the floor because Earth's mass curves the space-time beneath your feet. Gravity isn't acting on you at all. You're merely following the straightest possible line through a curved geometry. What we experience as weight is really the resistance of the ground stopping us from taking that natural path. When Einstein finally published his theory in 1915, he had been working on it for a decade, struggling, doubting, rewriting, and dreaming. The result was something breathtaking, a set of equations that could explain Mercury's puzzling orbit, predict the bending of starlight around the Sun, and foresee the possibility of ripples in space-time, gravitational waves, long before we had any means to detect them. And yet, even Einstein couldn't see all the consequences waiting inside those equations. Within months, another mind, Carl Schwarzschild, working in the grim quiet of the First World War, would find the first exact solution to Einstein's new geometry. In that solution lived the seeds of black holes, white holes, and even bridges to parallel universes. But Einstein himself was not thinking of monsters. He was thinking of beauty, of how the cosmos had suddenly become a living fabric, a thing that breathes, curves, and feels. The old puzzle that had kept Newton awake at night had finally been resolved. There were no invisible threads reaching across the void. The universe didn't pull, it folded. And as we drift further into this story, that folding begins to deepen. Space itself starts to curve until it can no longer return to flatness. In the next step of our quiet exploration, we'll follow the soldier who, even amidst the thunder of war, found a way to solve Einstein's impossible geometry, and in doing so, glimpsed the first shadow of infinity. The path now carries us deeper into the heart of Einstein's vision, into a world where space and time themselves can bend, stretch, and breathe. Imagine for a moment that the universe is made not of stars and planets, but of something invisible and continuous, like the fabric of a vast soft sheet. If you placed a heavy marble at its centre, the sheet would dip and curve around it. Any smaller marbles rolling nearby would spiral toward the dip, not because the heavy one was reaching out to grab them, but because the surface beneath them had changed shape. This is how Einstein taught us to think about gravity. He saw the universe as a flexible stage that responds to its actors. The more massive the actor, the deeper the curve it creates. And what moves along that curved surface is not just space, it's time as well. Everything that happens, from the swing of a pendulum to the orbit of a planet, unfolds within this woven fabric we call spacetime. It sounds simple, but the idea changed everything. In Newton's cosmos, space was a flat, endless backdrop, and time flowed the same everywhere. Einstein replaced that quiet emptiness with something alive. Space could warp, time could stretch. The universe was no longer a theatre, it was part of the performance itself. The relationship between matter and geometry is written in what physicists call the Einstein field equations, though here we can translate them into language rather than symbols. On one side, the equation asks about the contents of the cosmos. How much matter, how much energy, how it's moving. On the other side, it describes how space-time must curve in response. One side whispers, "Here is what exists." The other answers, "Then here is how I must bend." You might picture it like a conversation between weight and shape, between existence and form. If we could listen closely enough, the universe itself would be murmuring this dialogue everywhere, from the stillness between galaxies to the invisible depths of a black hole. Einstein's field equations can be written in a single line, compact enough to fit on one side of a postcard. Yet that single line carries more weight than any formula before it. It holds 10 interlocking relationships between geometry and energy, a whole family of equations bound together like threads in a tapestry. Solving even one of them exactly is an enormous challenge. Einstein himself could not find a perfect solution. He understood the melody, but could not play every note. And so, as the Great War raged across Europe, a letter made its way from Berlin to the Eastern Front, where a German astrophysicist named Karl Schwarzschild was serving as an artillery officer. In the noise and chaos of the trenches, Schwarzschild somehow found a few quiet hours to read Einstein's paper. Amid the thunder of distant guns, he took up a pencil and began to calculate. Perhaps, he thought, if he stripped the universe down to its simplest possible form, a single, unchanging sphere of mass, motionless in an empty void, maybe the equations would yield their first clear answer. He assumed the object did not rotate, did not shine, did not change. In the cold mathematics of war, it was the only kind of peace he could find. Working by lamplight, he wrote out the relationship step by step. what he discovered would change the way we imagine gravity forever. His solution described how space-time would curve around a perfectly round, uncharged mass, the simplest possible universe. Far away, where gravity was weak, the geometry would flatten again, like the sheet of fabric returning to stillness. But near the mass, the curves grew steep. The flow of time slowed, and space itself began to stretch inward. Schwarzschild's result was startlingly simple, so simple that Einstein himself doubted it could be right. Yet when the letter reached him, he was moved. He replied that he had not expected anyone to find an exact solution at all, much less one discovered under fire at the front. The shape of the geometry Schwarzschild found is something we can imagine without any math. Think of space as that same soft sheet, but now the marble at its centre has become impossibly dense, a star crushed into something far heavier than its size suggests. The closer you come, the steeper the dip in the sheet becomes. Time, too, begins to stretch, like a slow breath drawn out endlessly near the bottom of the well. If we could describe the solution in simple words, it would say something like this. At each point around this mass, the distance between moments changes. The closer you draw to the centre, the longer each second becomes, and the narrower the path that light can take. It was a quiet revelation. The universe could curve so deeply that even light, that messenger of all things visible, might fail to escape. At a certain distance from the centre, the slope of space-time would become infinite. This invisible boundary came to be called the Schwarzschild radius, the point where the escape speed equals the speed of light itself. In plain terms, it means this. If you were closer than that boundary, no amount of power could carry you away. Light itself would try to climb, but the slope would only pull it back. What began as a mathematical curiosity now hinted at something almost unthinkable. A region of the universe from which no signal, no glimmer, no memory could return. When Schwarzschild died only months later from illness, he never knew the true legacy of his work. To most physicists of the time, his solution seemed like a strange mathematical toy. After all, how could so much mass be crushed into such a small space? Nature, they thought, would never allow such absurdity. Even Einstein agreed. The equations might permit it, but the real universe surely would not. And yet, in the quiet logic of his numbers, the shape of the black hole was already there, waiting. The field equations had revealed not only a new way for space to curve, but a place where that curvature could become infinite, a place where time could fold back upon itself. It's haunting to think of it now, a man surrounded by war, drawing curves of space-time on paper, glimpsing the possibility of cosmic collapse while the world around him burned. What he found was both simple and terrifying, a universe that could, under the right conditions, swallow itself whole. As we drift onward, that idea will begin to unfold. The universe's quiet equations, once only abstract lines of thought, will now find their first reflection in the dying hearts of stars, and through their collapse, we'll begin to see that the mathematics was never just theory, it was a prophecy. From here, the story opens into one of the quietest and most haunting discoveries in all of science. A story that began not in a laboratory, but on a battlefield. While shells rumbled in the distance and the winter air hung heavy with smoke, Carl Schwarzschild sat beneath a dim lamp, his fingers stained with ink and graphite. In a lull between calculations for artillery trajectories, he turned his mind to Einstein's newly published equations. It was 1916, and the world outside was tearing itself apart. Inside his tent, another world was being born, one that curved inward upon itself. Schwarzschild's approach was disarmingly simple. He imagined the universe reduced to a single, perfect mass, spherical, unchanging, and utterly alone in empty space. Nothing else existed, no motion, no light, no noise. If Einstein's mathematics truly described the relationship between matter and geometry, then this bare, silent universe should be the simplest possible test. What shape would space-time take around such a solitary mass? After weeks of work, he found an answer. The equations, though often wild and uncooperative, had finally yielded. His solution described how space bends not only around a planet or star, but around any mass, even one compressed into a point. At first glance, the result seemed graceful, almost gentle. Far from the mass, space was nearly flat. Time flowed normally, and all was calm. But as you moved closer, the geometry began to twist. The deeper you went, the stranger it became, until the math itself seemed to tremble. Schwarzschild noticed that two particular places caused trouble. At the very centre, where the distance to the mass's heart dropped to zero, his equations blew apart. A true singularity, where curvature became infinite and the language of physics fell silent. That might have been expected. After all, no one could imagine what happens when matter collapses into perfect density. But then came the surprise. There was another point, not at the centre, but at a certain distance from it, where the math misbehaved again. There, one of the terms in his equation suddenly divided by nothing, a forbidden act that sent everything to infinity. Was the universe truly so unkind? Was there another catastrophe lurking at this invisible boundary? He wrote carefully to Einstein, explaining what he had found, and Einstein, reading it days later, smiled in disbelief. The solution was exact, astonishingly elegant, and yet it seemed to predict something impossible. At one radius, space-time itself appeared to fold into an abyss. Nothing, not even light, could climb out. The escape speed there was equal to light's own velocity. Cross that invisible surface, and every path, every possible motion, would lead only inward. In today's language, we call that invisible threshold the event horizon. But in Schwarzschild's time, it was simply a mystery, a mathematical cliff. Many physicists dismissed it as a trick of coordinates, a flaw in the map, not in the territory. At one distance, you could almost hear Schwarzschild saying, "The numbers go wild, not because space explodes, but because our compass loses its direction." And yet the more carefully others studied his work, the more they realised that this was no ordinary illusion. Inside that surface, all paths truly did point inward. No light could escape because there was no longer any outward to go toward. The horizon was not a wall, not a barrier, but a strange turning point in the structure of time itself. To picture it gently, imagine space-time as a smooth funnel made of velvet. Far from the centre, the slope is shallow. You could place a marble there, and it would roll lazily around, tracing orbits much like the planets around the sun. Closer in, the slope deepens. The marble moves faster, caught in a tighter circle, and then, just beyond a certain rim, the funnel drops away so steeply that no amount of speed can carry the marble back up. That rim is the Schwarzschild radius, the edge of no return. At first, no one believed nature would ever make such a thing. The mathematics might allow it, yes, but surely the universe was too well behaved. The idea that a star could collapse so completely that its light could vanish behind a horizon felt absurd. Einstein himself wrote that these singularities did not exist in reality. They were curiosities, not creatures of the cosmos. Still, the beauty of the solution refused to go away. The equations didn't argue or protest. They simply sat there, calm and complete, quietly insisting that if enough mass were packed into a small enough space, the result would be inevitable. The universe, it seemed, had a kind of secret threshold, a place where gravity no longer asked for permission. Schwarzschild died of illness before the war ended, never knowing what his discovery would become. But his simple solution, written in the chaos of conflict, became the seed of something vast, the first hint of what we now call a black hole. Even in its earliest form, the idea carried a strange poetry, the concept of light, that fastest, freest traveller, meeting a place from which it could never return. The notion of time itself slowing, curling and falling inward, like a leaf caught in a whirlpool of its own making. In this quiet geometry, Einstein's vision revealed not only the structure of gravity, but also the possibility of endings, of places in the cosmos where the story could go no further. We can soften the mathematics into a single human sentence. As you draw nearer to this invisible edge, space stretches like taffy, time lengthens like a breath held too long, and light itself bends until it can no longer find its way home. That is the essence of Schwarzschild's discovery, the first hole in space, carved not by violence, but by thought. It would take decades for astronomers to find evidence that such abysses were real. For now it remained an elegant ghost in the mathematics, a whisper beneath Einstein's grand symphony. But every whisper leaves an echo, and the echo of Schwarzschild's work would travel far, into the hearts of collapsing stars, into the soft glow of galaxies, and into the dreams of those who wondered what might lie beyond the horizon. As we drift further into the story, the focus will shift from paper and ink to the blazing hearts of real stars, the ones whose own gravity drives them inward, folding their matter like origami until they vanish from sight. In that collapse, Schwarzschild's strange geometry will come alive. The sky will learn how to make darkness, and the universe will learn how to hide its light. Our quiet exploration now turns toward the stars themselves, the glowing engines that fill the sky and make night feel alive. Every point of light you see above you is a furnace, an enormous balance between two opposing forces. Gravity pulls inward, always hungry, always patient. Radiation pushes outward, born from the burning of hydrogen into helium and heavier elements. The star survives only because these two powers agree to a fragile truce. Gravity trying to collapse it, fusion pushing back against the fall. For millions, even billions of years, this balance holds. But no peace lasts forever. Eventually the star's fuel runs low, its fire fading as the hydrogen in its core is exhausted. When the last of the light elements are fused, gravity begins to win. The star starts to shrink, its outer layers collapsing inward. What happens next depends on how massive the star was to begin with. For stars like our Sun, the collapse ends with grace. As their cores shrink, they heat again just enough to ignite new fusion shells, puffing up their outer layers. These layers drift away gently, forming colourful planetary nebulae, vast clouds of glowing gas that float like soft ghosts through the darkness. What remains behind is a dense, white ember, a white dwarf. In that ember, matter has been pressed so tightly that electrons, the tiny particles that usually dance freely around atomic nuclei, are squeezed shoulder to shoulder, refusing to occupy the same space. Physicists call this effect electron degeneracy pressure, but we can picture it more simply, a kind of invisible protest by matter itself. As gravity presses inward, the electrons push back, whispering, "We can move no closer." This is the law that keeps a white dwarf from collapsing further, a quiet equilibrium made not of heat, but of quantum rules. It's a remarkable thing, a star that no longer shines through fusion, yet resists destruction through the strange stubbornness of its smallest parts. The existence of such stars was first suggested by the physicist Ralph Fowler in the 1920s, after astronomers noticed one particularly faint companion orbiting the bright star, Sirius. That pale hot ember was named Sirius B, the first white dwarf ever confirmed. For a time, this seemed to solve the puzzle of stellar death. Gravity could be tamed, at least for ordinary stars, but there was a limit waiting in the shadows. A young Indian physicist named Subrahmanyan Chandrasekhar found it while sailing from Bombay to England in 1930. He was just 19, crossing the ocean to study with the famous Arthur Eddington, when he began to calculate how much mass a white dwarf could support before its electron pressure gave out. During long days at sea, he scribbled on sheets of paper, watching equations spill into strange territory. The results told him that there was a boundary, roughly 1.5 times the mass of our Sun. Above that, no amount of quantum resistance could hold back gravity. Beyond this Chandrasekhar limit, the star would continue to collapse. He presented his findings to the Royal Astronomical Society, only to be publicly dismissed by Eddington, who declared that there should be a law of nature to prevent a star from behaving in such an absurd way. The room laughed, but the numbers did not. They waited patiently, as numbers always do, for the universe to agree with them. When a star heavier than this limit exhausts its fuel, electrons and protons are crushed together by gravity, forming neutrons and releasing floods of ghostly particles called neutrinos. What remains is a ball of neutrons packed so tightly that a teaspoonful of it would weigh 1 billion tons. This is a neutron star, another temporary truce between gravity and matter. Here, it's the neutrons, not the electrons, that refuse to share the same space. Their own quantum pressure holds the collapse at bay. For a while, astronomers thought that might be the final chapter. Even massive stars would stop collapsing eventually. Nature, it seemed, always found a way to say, enough. But in 1939, two young physicists, J. Robert Oppenheimer and George Volkoff, discovered that neutron stars too have their limits. Beyond about twice the mass of our Sun, even neutron pressure cannot resist gravity's demand. Oppenheimer and another collaborator, Hartland Snyder, went further still. They described mathematically what happens when nothing can stop the fall. In their model, the star continues to shrink without end. To an observer far away, it seems to slow, its light reddening and fading, freezing just above the boundary, just as Einstein's equations predicted. But to the matter within, time itself continues to flow, and the collapse carries on relentlessly toward a singularity, a point where density and curvature become infinite, and our familiar laws break apart. When Oppenheimer and Snyder published their results, the idea was too strange for most to accept. Even Einstein objected. He believed that something must intervene before such a catastrophe could complete itself, some new physics that would prevent a star from vanishing entirely. To him, a black hole was a mathematical curiosity, not a real object. The notion of a body collapsing indefinitely offended both his intuition and his sense of symmetry. But the equations did not share his discomfort. They whispered quietly of inevitability. When mass passes a certain threshold, collapse is not an option, it is destiny. The very structure of space-time ensures it. You can think of it this way: a star is like a candle burning against its own weight. As long as it burns, the heat pushes outward, holding the waxy walls from caving in. But once the flame dies, gravity remembers what it was promised. It begins its slow work of returning everything to its simplest form. The outer layers may explode in a supernova, a brief blinding flash brighter than a galaxy, but the heart, the dense core, continues inward. The atoms that once sang with fusion fall silent, their particles merging, their spaces erased. It's as if the star folds itself like a piece of origami, each layer collapsing into the next until all that remains is a single, impossibly dense knot. What happens at the centre of that knot, no one knows. Einstein's geometry, so successful everywhere else, can't see inside it. Space and time, usually distinct exchange places, directions lose their meaning. The equations point inward but give no map of what lies beyond. The universe, it seems, keeps one last secret to itself. It's strange to think that the death of something so luminous could create a kind of perfection. Not chaos, but order taken to an extreme. In that silent, invisible core, gravity wins not by force, but by patience. It waits through billions of years, burning through layers of resistance, until finally everything falls in line. And so the stars that once filled the heavens with light become the architects of darkness. Out of their surrender comes something new, a horizon, a boundary, a place where even time bows its head. The mathematics that began as ink on paper now exists in the night sky, in the unseen hearts of galaxies. As we follow this thread a little further, we'll find that Einstein's predictions, once dismissed as absurd, begin to mirror reality itself. The horizon that seems so absolute, so final, may not be what it appears to be. Like a mirage on the edge of the desert, it might only be a trick of perspective, a wrinkle in our map of space-time. And as we look closer, we'll discover that the boundary between falling and frozen, between inside and outside, is not a wall at all, but a question. The path now carries us toward one of the most beautiful illusions in physics, a place where mathematics, perspective, and the flow of time weave together into something that looks impossible yet remains perfectly consistent. It is the story of the event horizon, the mysterious edge of a black hole, and of Einstein's final misunderstanding, a place where even he, the man, who bent space and time, was fooled by the very language he had created. When Oppenheimer and Snyder described a collapsing star in 1939, Einstein read their work and shook his head. He had seen the equations, but he could not accept what they implied. To him, the horizon, that invisible line where light can no longer escape, looked like a barrier. From his coordinates, the star seemed to slow forever as it approached that edge. The flow of time in his calculations stretched thinner and thinner, like honey poured onto glass. It never quite crossed. It simply faded, slowed, and froze. In his eyes, nothing could ever truly fall in. But this strange stillness, the freezing of time, was not reality itself. It was a trick of the map he was using. The horizon's singularity, that apparent infinite slowdown, was not a physical blow-up of nature, but a wrinkle in the coordinates, a misunderstanding of perspective. To see why, imagine trying to draw the surface of the Earth on a flat map. No matter which projection you choose, you can never represent every feature perfectly. The Mercator projection, for example, preserves the shapes of continents, but stretches them terribly near the poles. Greenland, which is only a fraction of Africa's size, looks nearly equal to it. The Gall-Peters projection fixes the sizes, but distorts the shapes instead, making the continents look tall and narrow. Both maps describe the same planet, yet both tell slightly different lies. Space-time maps are no different. Einstein's coordinates, the ones he first used to describe his equations, were like the Mercator projection. They made certain things easy to see, but at the cost of others. Near the event horizon, they broke down completely, showing infinities that weren't really there. Later physicists learned that by changing coordinates, by reprojecting space-time, the horizon becomes perfectly smooth. Nothing infinite, nothing catastrophic, just a quiet threshold. In one such system, called Kruskal-Sekaros coordinates, the equations reveal what really happens. The horizon is not a wall but a gentle crossing. Time doesn't stop there, it simply flows differently, much like the current of a river bending around a rock. From the point of view of an outside observer, an infalling object takes forever to reach the horizon. But for the traveller falling in, the crossing happens in a heartbeat, unnoticed. It's the difference between watching someone drift away down a river and being carried along by the current yourself. To the one standing on the bank, the swimmer seems to slow as they near the horizon of sight, their strokes stretching out in time. To the one in the water, nothing changes. The current carries them on, and the river flows as it always has. You can imagine it softly. Space itself behaves like a moving stream. Far from the black hole, the current is slow. Light can swim against it. As you draw nearer, the flow quickens, and the photons, those little swimmers of light, must struggle harder to move upstream. At the event horizon, the river of space flows inward at exactly the speed of light. The photons released right there can hover forever, neither escaping nor falling in, like fish caught in an invisible eddy. And inside the horizon, the current outruns even light. No matter how fast you swim, the flow carries you onward, inevitably, toward the centre. This is the waterfall model of space-time, a vision so clear that it can almost be felt. If we could look at it from above, we'd see space plunging inward like a smooth cascade, carrying everything with it. The horizon is not a solid edge, but the point where space itself falls faster than light can climb. The fall continues endlessly until it meets the singularity, the place where the river ends and time itself folds. Einstein, if he could have seen this picture, might have smiled. His mistake was not a failure of intellect, but of perspective. The horizon that he thought was frozen was, in truth, an artifact of the coordinates, the same kind of distortion that makes Greenland look enormous. The universe, as it turns out, does not care which map we use. Reality remains smooth and calm beneath our errors. There's something profoundly comforting in that. The mathematics may twist and warp, but nature itself is steady. The horizon is not a curtain being drawn, but a point of view shifting its angle. For the observer watching from afar, the falling star becomes fainter and slower, as if time itself has thickened. For the traveller falling in, the horizon rushes up and passes by without so much as a whisper. Both are right. Both are true. The difference is not in what happens, but in how it is seen. If we describe this softly, without symbols, the story reads like this. From the outside, time stretches until it nearly stops. From the inside, it flows onward without pause. The horizon is not the end of the story. It is merely a page seen from two directions at once. The revelation that the horizon was not a true singularity was one of the quiet triumphs of 20th century physics. It showed that Einstein's equations were not broken. They were deeper than even he imagined. The coordinate singularity, as it was called, had never been a tier in space-time, only a fold in the language we use to describe it. The event horizon remains, however, an extraordinary concept. It's the ultimate one-way door, the perfect embodiment of a symmetry in the universe. Matter, light, and information can cross it inward but never return. To an external observer, the surface of the black hole holds a frozen image of everything that has ever fallen in, imprinted in red-shifted light. Inside, those same objects continue to fall, unaware of the frozen reflections they leave behind. The horizon is where these two realities touch, a quiet meeting place between stillness and motion. Even in its mystery, it obeys a beautiful consistency. No contradictions, no chaos, just two sides of the same truth seen from different vantage points. When we say that reality is relative, this is what we mean. Not that it's uncertain or unstable, but that every observer carries their own slice of the cosmic story, each one complete, each one true. And so, what Einstein once thought was a wall turns out to be an illusion of coordinates, a lesson that our maps can mislead us, but the terrain remains serene. It's a gentle reminder that even the greatest minds can be tricked by perspective, and that the universe always has one more layer waiting to be unfolded. From here, the story deepens once more. We've seen how a black hole bends the flow of time, how light struggles against the river of space. But the mathematics still hides more. Structures that connect universes, pathways that stretch beyond horizons, and reflections of reality that move backward in time. As we drift further into this exploration, we'll begin to see space-time itself, not just as a fabric, but as a living map of light and destiny. As we move gently to the next bend in the path, the story begins to turn luminous again. To understand the shape of time itself, we need to see how light moves through the darkness. In Einstein's universe, light is not only what reveals things, it defines what can be revealed. It draws the boundaries between past and future, between what can happen and what cannot. Imagine standing alone in the middle of a vast quiet plain on a moonless night. You strike a match, and in that instant a small flame flickers into being. Its glow expands outward in all directions, a gentle sphere of possibility growing through the dark. Now imagine that we freeze this scene at every instant, each thin shell of light as it spreads farther and farther from you. If we could stack these moments on top of one another, the shells would trace out a shape, a cone made of light. Physicists call it a light cone, though it is less a thing than a rule. It marks the region of spacetime that your action, that single spark of a match, can ever influence. Everything inside the cone is reachable by some path through space and time. Everything outside it will remain forever untouched. The past, too, has its cone, the inverted reflection of the same shape, containing all the events that could have influenced you before this moment. Together, these two cones form your private portion of the universe, the slice of reality connected to you by light. In the empty flatness of ordinary space, these cones open at a familiar angle. Light, the fastest messenger, travels along the edges, while slower things, you, the earth, your thoughts, move within. But around a massive body, the geometry of space begins to tilt. The light cones lean toward the mass, as though gravity were whispering to them, pulling them gently inward. Near a black hole, that tilt becomes extreme. The future itself, defined by those cones, begins to point toward the centre. It's a strange picture, but a comforting one too. It means that near something massive, down and future become the same direction. Falling is not a loss of control. It is simply the natural flow of time in curved space. In the end, everything that moves follows the same rule. It drifts along the surface of its light cones, always inward toward its own future. If we describe this softly, we might say, the light cone is the lantern each event carries, showing what it can touch, what it can become. As gravity deepens, the lantern tilts, and the circle of its light grows narrow, until the only direction left to shine is inward. Einstein's field equations, once too abstract to imagine, now take on a picture. They tell us not just how space curves, but how the flow of cause and effect, the ordering of events, changes shape. The cones are not static. They warp and lean depending on how spacetime itself is bent. And this bending is what gives gravity its quiet power. There is no force pulling you down to Earth. Rather, the shape of time itself bends such that downward is simply what forward in time means in this neighbourhood of space-time. To visualise this more gently, think of yourself as a drop of rain sliding down a tilted window pane. The rain is not pushed downward, it simply follows the slope that's already there. In Einstein's view, every bit of mass creates its own tilt in space-time, guiding other things along their natural paths. The heavier the mass, the steeper the slope, and the narrower the light cones become. In the calm emptiness of space, far from any mass, your future spreads open. You have many directions you might go, many possible choices. Near a black hole, those possibilities close like a folding fan. Every line of the future leans toward the abyss, and light, the most restless traveller of all, cannot help but follow. This vision of tilted light cones may sound abstract, but it's one of the most profound insights of relativity. It shows that gravity and time are not separate effects, but different faces of the same geometry. When gravity grows stronger, time slows down. When space-time curves, the definition of forward itself changes. Every clock, every photon, every heartbeat follows its own tilted path. If we could make this visible, we'd see a universe filled with invisible lanterns, each one a point in space-time, each one shining its future and past cones through the dark fabric around it. They would overlap, merge and twist together, forming a delicate lattice of connection. Every event, no matter how small, lights its own piece of reality. You are within millions of such cones right now. The light from distant stars touching your eyes, the warmth from the sun that began 8 minutes ago reaching your skin, the faint radio waves from galaxies crossing oceans of time to whisper through your devices. Each one threads its light through your moment. To Einstein, these cones were not mere drawings. They were the skeleton of causality, the very structure of what can happen. And as strange as they are, they also preserve a deep kind of order. Even in the chaos of collapsing stars and spinning black holes, the light cones remain consistent. They tilt, stretch, and narrow, but they never break. They are the universe's way of keeping time honest. It's humbling to realize that every single thing you've ever seen, every sound you've ever heard, every feeling you've ever had, is something that lived inside your past light cone. The rest of the cosmos, the stars whose light hasn't reached you yet, still lies outside, waiting. To see them is to wait for time itself to unfold a little further. In the gentle rhythm of the cosmos, light becomes both messenger and boundary. It is what lets us see and what stops us from seeing. It defines the line between before and after, between here and elsewhere. The cones of light are, in a way, the universe's punctuation marks, pauses between what has already been written and what is still being composed. So when we speak of spacetime diagrams, those simple drawings of cones and lines, we are really talking about portraits of possibility. They show us that every event is both cause and effect, every moment a crossroad, and when gravity bends these cones, it's as if the universe were editing its own sentences, changing what can touch what, rewriting the rhythm of cause and effect. As we drift further along this thread, the picture will become even more fluid. We will see that space itself, not just the objects within it, can move, flowing like a slow river into a black hole's depths. Light will become the swimmer, time the current. The cones we've drawn will turn to streams, and we'll watch as the universe reveals that falling, in the deepest sense, is simply the motion of space itself. Our quiet exploration now turns toward a picture so simple, and yet so strange, that once you see it, it never leaves you. Imagine standing beside a vast, dark waterfall, not of water, but of space itself. You can't see it, but you can feel its pull, a silent flow that draws everything inward. This is how physicists sometimes describe what happens near a black hole. Space is not standing still. It is moving, falling, like a great invisible current. In the emptiness far from any massive object, space sits still. You could imagine it as a calm lake, perfectly flat where light travels straight and steady, and time ticks at its ordinary pace. But as you drift closer to something massive, the lake begins to slope, then tilt, then rush. Space starts to flow inward toward the object, and the closer you get, the faster it flows. At first, the current is gentle. If you were a beam of light, you could still swim against it and escape. But near the event horizon, the flow becomes so fast that even light cannot swim upstream anymore. It's not that light slows down, it always moves at the same cosmic speed, but that space itself, the stage on which everything moves, is rushing inward faster than light can climb out. This image, called the waterfall model of spacetime, helps us understand why black holes are not merely places where gravity pulls, but regions where reality itself is being carried inward. It's a shift in perspective. Gravity is not something acting on space, it's space in motion. The curvature that Einstein's equations describe, those elegant relationships between matter and geometry, can be imagined as this inward fall. You could picture photons as swimmers in this river of space. Far away, the current barely nudges them, and they can move freely in any direction. Closer in, They must swim harder to go outward, fighting the flow. At the horizon, the river of space moves exactly at the speed of light. A photon emitted outward here hovers in place, balanced perfectly against the current. And inside that boundary, the current wins completely. No matter how fast a swimmer moves, they are swept deeper inward. It's a beautiful paradox. Light never slows, yet still it cannot escape, because the river that carries it is flowing faster than light itself. The horizon is not a wall. It's the moment the current overtakes every possibility of return. You can imagine yourself drifting on this current, feeling the steady pull grow stronger. There is no sensation of falling, no sudden jolt. Space itself is carrying you, so you feel weightless, calm, as though floating in a dream. You could shine a flashlight upward, and the beam would seem to hang, frozen just above you, its photons trapped at the very edge of possibility. You could shout, but your voice, waves in the fabric of air and space-time, would never reach beyond that horizon. Outside observers, watching you drift toward that edge, would never see you cross it. To them, you would appear to slow, then fade, your image redshifting into deeper and deeper tones until it vanished. To you, nothing special happens. You drift across the horizon as easily as a fish glides past a point in the stream. From your perspective, it isn't the end of space. It's simply where the direction of down merges with the direction of forward in time. The two become the same. This is one of the quiet truths of relativity. What we call gravity is not a force pulling you down, but the way space-time guides everything along the simplest possible path. In this model, that path is the current of the river, always forward in time, always downward in the geometry of space. We can soften the mathematics behind this. The geometry of space-time near a black hole is defined by how fast this current of space flows inward. At the horizon, that flow equals the speed of light. Inside, it grows faster and faster, carrying everything toward the center, where our maps break down. If we could listen to the language of the equations, they would whisper, "The fabric of the universe moves here." What you feel as gravity is the drift of space itself. It's a strange way to think about reality, but it gives the illusion a beautiful clarity. The horizon is not a frozen wall. It is the surface where the flow of space matches the speed of light. Time, seen from far away, seems to stop there, but that's only because we are looking upstream against the current. For the one carried along, time moves normally, always forward, always inward. You can almost picture this as a cosmic waterfall. Near the top, where the flow is gentle, waves can ripple outward, but closer to the edge, the water moves so swiftly that nothing can climb back up. Cross the lip of the fall, and you are no longer moving through the water. The water is moving you. Inside the fall, space itself is the motion, the rushing veil that carries everything toward the hidden pool below. If you were to drop different objects, a pebble, a feather, a beam of light, they would all follow this same stream once they were close enough. No matter their weight or speed, each would be drawn into the same quiet plunge. That's why black holes treat everything equally. They are not choosy predators, but perfect listeners. They simply follow the rules of spacetime's flow. Even the concept of inside and outside becomes delicate here. For the outside observer, the horizon is unreachable. Nothing crosses it in finite time. For the traveller within, the horizon lies forever behind, the entrance to a region that no longer connects to the rest of the universe. The two stories coexist, both true, both complete, each belonging to its own point of view. Einstein's equations, when translated into this image of a flowing space, sound almost like poetry. They describe a cosmos that does not sit still but moves, breathes, and curves. Every star and planet is a tiny eddy in this flow, every orbit a gentle swirl in the larger current of the universe. If we could see it, space-time would not look empty or static. It would shimmer with motion, subtle waves of gravity stretching and compressing, ripples travelling at the speed of light, invisible yet real. And near black holes, those ripples deepen into an endless fall, the purest expression of motion itself. In the silence of this falling space, there's an unexpected kind of peace. The equations don't shout, they hum. They tell us that what we call attraction or pull is really harmony, a smooth alignment between time, motion, and geometry. Everything is falling together, not apart. So the next time you imagine a black hole, don't think of it as a violent tear in the cosmos, but as a gentle waterfall, an unending drift of reality itself, flowing inward. To stand near one, if such a thing were possible, would not feel like being dragged or crushed, but like surrendering to the quiet current of the universe. And from that image, our journey continues. If we could step back far enough to watch this great river from above, we would see how all the currents of light and gravity intertwine, how infinity itself can be folded into a single page of geometry. The universe, in its patience, has a way of turning vastness into simplicity. That is where we drift next, toward the art of mapping eternity. From here, the story opens into one of the most elegant tricks the universe has ever played, a way of showing infinity on something small enough to fit in the palm of your hand. It begins with a question physicists once whispered to each other late at night. How can you draw a map of something that has no edges? When you look up at the night sky, every star seems to exist on a distant dome above you, but in truth, there is no dome, no shell. The universe stretches outward endlessly, and time too extends in both directions, into a past we can barely glimpse and a future we can only imagine. Trying to picture such immensity is like trying to capture the sea in a teacup. You can only ever hold a reflection. Physicists needed a way to visualize this unending landscape, especially near black holes, where space and time behave in such counterintuitive ways. Ordinary coordinates, the kind that describe up, down, and distance, simply fail. A black hole distorts them until they twist in knots. So, they looked for a new kind of map, one that could show the whole story, from the edge of infinity to the heart of the singularity, on a single sheet. The answer came in the form of something called a Penrose diagram, named after the mathematician Roger Penrose. But for our journey, we can think of it as the universe's most elegant doodle, a sketch that turns eternity into geometry. Imagine gently that you could take the entire timeline of the universe, infinite past, infinite future, and squeeze it into a single rectangle without losing the relationships between events. Time would flow upward, as it always does, but the infinite would be compressed, compacted the way a mapmaker squeezes continents onto a globe. Light would always travel at 45 degrees, halfway between up and across, preserving its role as the boundary between what can and cannot communicate. To make this clearer, picture a black hole as a kind of cosmic stage. At the top of the stage lies the singularity, the last possible moment of time where all paths end. At the bottom lies the infinite past, stretching beyond imagination. To the sides, infinitely far away, sits the outer universe, the quiet region where space flattens and light can wander freely. When you fold all of this onto a single page, these infinities curl gracefully toward the edges. The result is a shape that looks simple, almost childlike, triangles and lines crossing in symmetry. Yet it contains everything: birth, death, and all the curved in between. What the Penrose diagram shows better than any formula could is the architecture of destiny. It reveals where each path through space-time begins and ends, and which paths can ever meet. In the region outside the horizon, light can travel outward to infinity, meaning signals can still escape. Inside, the lines of the future all tilt toward the singularity at the top. Every possible journey ends there. The horizon itself appears as a diagonal line between these regions, a gentle divider between freedom and inevitability. When you look at this map, something almost paradoxical appears. The singularity is drawn not as a point, but as a line, a stretch across the top of the diagram. It represents not a location in space, but a moment in time, the final one for anything that falls within. In other words, the singularity is not a place you can go to, but a time you will reach. It's the ultimate tomorrow. The brilliance of this map lies in its humility. It does not claim to show distances or sizes, only relationships. It is, at its heart, a map of connection. 2 points that can exchange a beam of light lie within each other's cones. Those that cannot do not. By folding infinity into a finite picture, the Penrose diagram reminds us that the universe's vastness can be understood through structure rather than scale. If we describe this softly, the diagram is a meditation on perspective. The infinite, when folded gently, becomes a pattern, a reminder that even forever has its geometry. This compact way of seeing the cosmos doesn't just help physicists calculate, it helps them feel. When they trace a line on that page, the line of a falling particle, or a beam of light curving into the hole, they are watching the story of space and time unfold in miniature. They can see how, once inside the horizon, all paths converge upward, never outward. They can see how even the speed of light cannot break the angle that destiny has set. And perhaps most beautiful of all, they can see symmetry. The same geometry that describes a black hole's interior also hints at its mirror image, a white hole, where the arrows of time reverse, and things can emerge but not enter. On the Penrose map, the two look almost like reflections across a line of light, twin halves of the same equation, forever balanced and forever apart. Standing before such a diagram, you might feel something unexpected. Peace. There is order here, hidden beneath the chaos we usually imagine around black holes. Every path, every tilt of light, follows the quiet logic of geometry. Even the singularity, the place where our equations stop making sense, has its assigned place on the page. It's not wild, it's simply beyond what the map can show. If you trace your finger along the outside edge of the diagram, following the boundary where light can still escape, you're tracing the story of everything we can ever observe, the portion of the universe that remains visible to us. Beyond that line lies the rest, the unseeable, the unreachable, the regions of space-time cut off from our future. The Penrose diagram is, in a sense, the most honest map ever drawn because it admits its own limits. It shows us that every observer lives within a finite view, no matter how infinite the reality beyond. For a moment, it's worth pausing here, imagining how it feels to draw infinity into something small. It's like folding a blanket of stars until you can carry it in your hand, like compressing every story ever told into a single hum of understanding. The physicists who first drew these diagrams were not just calculating, they were translating awe into ink. So if the waterfall model taught us that space can move, the Penrose diagram shows us that even motion has a shape. It tells us that all things, light, matter, time itself, travel along lines of possibility that begin somewhere, end somewhere, and are always connected by the same rules. Even eternity, it seems, can be drawn, as long as you're willing to fold it. And as we leave this map behind, the story will begin to open outward again. The quiet geometry of the Penrose diagram hints at something deeper, the realization that the universe, in its equations, is capable of mirroring itself. For every black hole, there exists a theoretical opposite, a reflection of time where falling becomes rising, where what once could not escape is instead compelled to emerge. As we drift into that mirrored world, we step softly into the realm of white holes, the other side of gravity's dream. The story unfolds a little more, leading us onward. The map we just folded begins to shimmer, as though the universe were quietly showing us its reflection. Every equation has two sides after all, and in Einstein's mathematics there is no preferred direction for time. The laws work just as well forward as backward. If a black hole is a place where things can fall in but never escape, then by simple symmetry there must exist its twin, a place where things can only leave and nothing can enter. Physicists gave this mirrored possibility a name, the white hole. It sounds like a fantasy, and perhaps it is. Yet within the equations it appears as naturally as a reflection in water. If the black hole represents the universe inhaling, pulling matter and light inward until they disappear, then the white hole is the exhale that never began. It is the same geometry, but with the arrows of time reversed. Imagine for a moment watching a recording of a black hole played backward. The dark centre, once swallowing everything, now spits out streams of matter and light. The horizon, which used to trap every photon, becomes a barrier no object can approach. Everything that was once lost returns, but not because it was freed, simply because the flow of time itself has reversed. What once fell in is now emerging. What once dimmed and vanished now brightens and departs. In that mirror world, a white hole shines fiercely, not because it burns, but because it expels. It doesn't radiate energy the way a star does. It's not fusing or glowing, but because, by definition, everything that reaches its horizon must move outward. Its light is the echo of the universe itself trying to reverse its breath. If we could translate Einstein's equations into words soft enough for the ear, they might say, time may flow either way, as long as space curves in kind. In the mathematics, both black and white holes are simply halves of a single possibility, joined like inhalation and exhalation in a cosmic breath. To make sense of this, imagine space and time as a vast landscape of hills and valleys. A black hole is like a pit, deep and steep, from which nothing can climb. A white hole is the opposite, a peak so high and slippery that nothing can descend. Both shapes obey the same geometric rules. They're just the same hill turned inside out. But there's a reason we find only one of them written across the sky. Nature, as far as we can tell, chooses a direction for time. We live in a universe that remembers its past but not its future, where cups fall and shatter but never leap whole from the floor. It's a world where order quietly decays into disorder, where stars burn out and entropy rises like the tide. In such a universe, white holes seem like polite impossibilities, beautiful but unwelcome guests. To exist, they would need time itself to flow the other way, so that entropy decreases instead of grows. The light leaving a white hole would be more organised, more perfect than the light that entered the black hole that preceded it. It would be the reverse of decay, an explosion of increasing order, like a shattered vase reassembling itself mid-air. And yet, there's something mesmerising in the symmetry. The math doesn't forbid them, it simply doesn't encourage them. White holes exist comfortably in theory, as long as you don't demand that nature make one. They're like dreams that the universe allows on paper, but keeps safely out of reach in reality. To picture one gently, imagine standing on a dark plain and watching the air begin to glow. From a single point, a storm of light and matter bursts outward, not like an explosion with a cause, but like a memory playing backward. Dust that was never there suddenly flies past, forming patterns that seem to uncollapse into existence. Everything races outward faster and faster, and at the heart of it all, the brightness grows unbearable, as if the universe were coughing up its forgotten moments. If you could pause that instant, you might realise that nothing truly new is being created. The white hole is simply returning what the black hole once took, only in reverse order, as if rewinding, the film of creation itself. But the problem is that the universe does not like rewinding. Its entropy, that soft measure of disorder, resists. For a white hole to persist, it would need a kind of perfect balance, a reversal so precise that not a single atom drifted off course, and perfection in the physical world is as fleeting as a breath on glass. So physicists tend to treat white holes as mathematical curiosities, necessary for the completeness of the equations perhaps, but not as residents of our cosmos. Still, their existence in theory opens the door to deeper dreams. Because if time can run in both directions, and if space can bend enough to make one horizon that swallows and another that expels, then maybe there's something between them, a bridge, a tunnel, a place where one side becomes the other. And indeed, in the quiet corners of Einstein's mathematics, such a connection appears. A single solution, fully extended, reveals not only a black hole and a white hole, but also two separate universes connected by a narrow throat. It's a tunnel made of geometry, not matter, a bridge through space-time itself. Later, this bridge would be given a name that sounds almost whimsical, the Einstein-Rosen Bridge. But before we reach that, it's worth lingering for a moment on what the white hole represents, even if it never truly exists. It is the reminder that the universe, in its logic, never favours one direction absolutely. What falls could, in principle, rise. What collapses could, in the mirror of mathematics, expand. Every curve has its reflection, every shadow its inverse. We can think of it as the universe's built-in poetry, a kind of symmetry that need not be real to be meaningful. Because in a way, the white hole tells us something about black holes themselves, that even the deepest collapse carries the mathematical possibility of reversal. The universe may not grant it in practice, but it leaves the door open in theory, just wide enough for wonder to slip through. So perhaps it's not that white holes are forbidden, but that they belong to a different kind of universe, one whose time flows opposite to ours, whose stories begin where ours end. Maybe, somewhere in the vast landscape of possibilities, such a universe breathes out while ours breathes in. As we drift further into this reflection, the picture will expand again. The geometry that gave birth to both black and white holes can stretch, fold, and join two universes through a common throat. It's an idea so strange that even Einstein hesitated to believe it, a bridge not made of stone or steel, but of space-time itself. Two skies stitched together by a moment too brief to cross. As we drift further into this quiet geometry, it becomes clear that what we've been exploring is only half of the picture. The maps we've used so far, even the beautifully folded Penrose diagrams, show just one side of the universe's landscape, a single hemisphere of space-time. The equations that describe a black hole, elegant as they are, hide another region beyond their edge, a counterpart as symmetrical and invisible as the far side of a globe. To understand it, imagine the Earth seen from space. When you look down at one hemisphere, the northern, say, you can see continents, oceans, and the arc of the horizon. But the southern half is hidden beneath the curve. The planet, however, doesn't end there. It simply continues beyond your line of sight. The same is true for Einstein's geometry. The standard coordinates that describe a black hole, the ones Schwarzschild first wrote down, cover only one side of space-time's sphere. They stop at the event horizon, as though the rest of the world simply ceases to exist. But when mathematicians extended those coordinates, something remarkable appeared. A second region, perfectly symmetrical to the first. This new domain wasn't a continuation of the same space, but an entirely separate one. Another universe, if you like, connected through a narrow throat. It was as if the northern hemisphere of space-time had been mirrored across the equator, revealing a southern half that could only be reached through the heart of the black hole. Einstein and Nathan Rosen, working together in 1935, studied this extended geometry and realized what it meant. If you take the equations that describe a black hole and unfold them fully, not stopping at the horizon, you find two exterior universes connected by a single passage. This passage isn't made of matter or energy, it's purely geometric. a tunnel woven from the curvature of space-time itself. They called it a bridge. Later, physicists would give it a more lyrical name, the Einstein-Rosen bridge. To picture it softly, imagine two distant skies, two separate universes, each complete in itself, each with its own stars, its own timeline, its own vastness. Between them lies a narrow throat, curved inward on both sides like the waist of an hourglass. The bridge connects the two universes at their centres, the place where the fabric of space pinches tightest. If you were to fall toward the black hole in one universe, your path would carry you down into that throat. And if you could somehow survive the crossing, you would emerge into the other universe through what, to its inhabitants, would appear as a white hole, the mirror twin we met before. Matter would seem to burst outward, light would flow freely away, and time would appear reversed. From one side you would be falling in, from the other you would be rising out. It's an astonishing symmetry. The black hole on one side of the bridge swallows light. The white hole on the other spits it out. One consumes, one emits. In the equations, the two are united, balanced across the narrow waist like mirror images facing each other. But this bridge is not a tunnel through which travellers could stroll. The geometry is delicate, almost fragile. The throat that joins the two universes exists only for an instant of coordinate time. From the point of view of any real observer, it pinches off before anything can pass through. The connection is there in the math, but not in the physical world. To describe it gently, we might say, the Einstein-Rosen bridge is a conversation between two universes, but one spoken so quickly that no message can be heard. Even so, the idea captured imaginations everywhere. For the first time, physicists could imagine space not as something continuous and infinite, but as something that could fold and touch itself. Distant regions connected not by distance but by geometry. It was as if the universe had discovered a new way to write poetry, using curvature instead of words. In the decades that followed, this image of the bridge began to take root beyond physics. Writers, philosophers, and dreamers borrowed it as a symbol of connection, of hidden paths between worlds, of unseen links between minds or moments. The phrase wormhole came later, inspired by the simple idea of a worm tunnelling through an apple. Rather than crawl around the surface, it digs a shortcut straight through the core. And so the Einstein-Rosen bridge became known as a wormhole, a tunnel of space-time connecting distant points, or perhaps even distant universes. It's a term that sounds almost playful, but the reality it points to is quietly profound. If such tunnels could exist and remain stable, they would change our understanding of distance entirely. Two stars on opposite sides of the galaxy could, in theory, be connected by a path shorter than the space between your hands. Yet, in Einstein's and Rosen's version, the bridge collapses too quickly to cross. Its geometry folds back in on itself like fabric snapping taut. You can imagine two skies stitched together by a moment too brief to pass through, a flash of connection that vanishes the instant it appears. The equations allow the bridge, but only as a fleeting possibility, like a spark of symmetry in an otherwise one-way universe. There's something poetic about that fragility. It reminds us that not all connections are meant to be travelled. Some exist only to show that even in isolation, everything remains part of a single pattern. The two hemispheres of space-time may never truly meet, yet they mirror one another perfectly. What falls in on one side rises out on the other. The universe, it seems, keeps its balance even when its halves cannot touch. Einstein himself was cautious about this discovery. He saw it less as a gateway between worlds and more as a clever mathematical trick, a way to remove the singularity that seemed to lurk at the centre of a black hole. But he could not have known that his bridge would one day become one of the most enduring symbols in both science and imagination. To think of space-time not as a static canvas, but as something that can fold, curve, and connect. That's where the real magic lies. The Einstein-Rosen bridge was a hint of that flexibility, a whisper from the equations suggesting that the universe may be more intertwined than it appears. If we could see it as a picture, it might look like a cosmic hourglass, its two bulbs filled with starlight instead of sand, joined by a narrow thread of geometry. On one side, time flows toward the future. On the other, time flows away from it. In that brief connection, the boundary between here and elsewhere, between before and after, almost disappears. It's easy to see why such an image captures us. It offers hope that the distances we feel between things, between people, between galaxies, are not absolute. That even the vastest separations might still be joined by something quiet, invisible and momentary. And so, as we drift onward, we carry that thought with us, that even space itself might once have touched another space, if only for a heartbeat of cosmic time. Yet the universe, careful and precise, does not let such shortcuts remain open. The bridge, though beautiful, collapses before anything can pass through. And that leads us softly to our next question. Could there ever be a way to keep it open? As we follow this quiet curve of thought, we come to one of the universe's most quietly tragic ideas, a bridge that exists only long enough to promise passage, but never long enough to let anyone cross. The Einstein-Rosen bridge, beautiful as it was on paper, turned out to be a fleeting illusion, a door that opens between two universes and then closes before even a single photon can step through. To understand why, imagine standing at the edge of that cosmic hourglass before you stretches the throat of space-time, curved, shimmering, drawn tight like the neck of a glass bottle. On one side lies your universe, with its galaxies, stars and rivers of time flowing steadily forward. On the other side lies its mirror, another universe, perhaps identical, perhaps utterly strange. Between them lies the passage, narrow, delicate, alive only for a moment. You might imagine yourself stepping into it, feeling the light of your own world fade as the curve of space bends around you. For an instant, you're suspended between two skies. You take a step forward, and then, before you can reach the other side, the bridge begins to vanish. The throat tightens, the passage shrinks, and the geometry folds back in on itself. The path you hoped to take was real for a heartbeat, and then it was gone. That's what the mathematics tells us when we translate it softly. The Einstein-Rosen bridge, in its original form, cannot remain open. The two universes it connects pull on each other like opposing tides, stretching the bridge thinner and thinner until it pinches shut. In Einstein's own equations, the throat collapses faster than anything could ever travel through it. To an outside observer, it doesn't just close, it never truly opens. One physicist once described it this way: you try to run across the bridge, but the bridge runs faster than you. It's a simple phrase, but it captures the quiet cruelty of space-time's precision. The moment you begin to enter, the geometry responds by curving inward, sealing the path ahead. You're always chasing an exit that retreats at the speed of light. In the language of the Kruskal-Sekeres diagram, that folded map we drew earlier, this looks like two triangles barely touching at their corners. They meet for an instant, sharing a single point of contact, and then drift apart forever. Each universe continues along its own line of time, unaware that it was ever connected. If you could somehow watch from outside the page, you would see that nothing actually falls through the bridge. Light sent into the throat never emerges on the other side. It simply circles the narrowest point, trapped in an infinite delay until the bridge closes completely. The equations don't break. They remain elegant and exact. But their message is clear. The passage exists only in mathematics, not in the living fabric of the cosmos. Still, there's beauty in this kind of impossibility. It reminds us that not everything real must be permanent. Even a fleeting symmetry has meaning. The bridge collapsing is not a failure of the universe. It's a reminder that time has direction, Our cosmos is not a static sculpture but a moving story, and every story must flow one way, from before to after, from possible to past. We can think of the Einstein-Rosen bridge as the universe's brief attempt at balance. It tried to connect two infinities, to join inhalation with exhalation, collapse with expansion. But time refused to hold still. The moment the bridge appeared, time itself tilted, and gravity pulled its structure inward. The tunnel became a trap, then a point, then nothing at all. If we soften the technical details, the collapse happens because gravity inside the throat acts like pressure in a straw. The very curvature that creates the bridge also ensures its destruction. The deeper the curve, the stronger the pull inward, until the walls of space-time can no longer resist their own weight. The tunnel caves in not from outside interference but from its own perfection. It's as though the universe built a bridge too elegant to survive. In the decades after Einstein and Rosen proposed their bridge, physicists kept wondering whether some version of it might endure. Could there be a way perhaps to hold the throat open? Could some force, or some exotic kind of matter, counteract gravity's instinct to close it? For a time, this question drifted like a quiet rumour among theorists, waiting for an age when mathematics and imagination could meet again. But before we reach those modern ideas, it's worth lingering on the image of the collapsing bridge, because it tells us something profound about the way the universe treats connection. In Einstein's geometry, every path that might lead to another world eventually narrows to a single timeline. There are no shortcuts through reality that last. Every attempt to bypass the distance between places is gently denied, as if the cosmos were protecting its own consistency. There's a theorem, written decades later, that formalised this principle. It's called topological censorship, a poetic phrase for a simple rule. The universe hides any shortcut that would let you cheat its causal order. You can imagine it as the cosmos tucking away its private hallways, ensuring that the story of cause and effect remains unbroken. If something could cross from one universe to another instantly, it would violate the rhythm of time itself, and the universe, like an author guarding its plot, refuses to allow that. So, the Einstein-Rosen bridge becomes a symbol of longing rather than travel. It's a reminder that not every equation needs to describe something you can touch. Some solutions exist only to remind us that symmetry and reality are not always the same. The bridge collapses, yes, but in doing so, it teaches us that even impossibility can be beautiful. Imagine looking up at the night sky, knowing that beyond those pinpricks of light are distances too vast for any ship to cross. And yet, in the folds of Einstein's equations, those distances shrink to a single curve. Two skies briefly touching, then drifting apart. The connection is gone, but the thought remains, as soft and persistent as starlight that began its journey long before we were here to see it. It's tempting to wish for the bridge to hold, to believe there might be some way through. And in a sense, the universe does leave that possibility open, faint, delicate, but not entirely closed. The same mathematics that doomed the Einstein-Rosen bridge would, years later, hint at another kind of bridge, one with motion, with spin, with a rhythm that might momentarily resist collapse. A bridge shaped not by stillness, but by rotation. Because when the universe spins, it changes the rules. Space doesn't just curve, it twists. Time doesn't just flow, it spirals. And in that swirling geometry, some doors that once shut too quickly might stay open just long enough to glimpse what lies beyond. As we drift onward, the story turns toward that spinning world, to the discovery of Roy Kerr's elegant solution, where black holes whirl like cosmic storms, and where the geometry grows so intricate that even infinity begins to fold back on itself. The path now carries us from stillness into motion, from the silent geometry of Schwarzschild's perfect sphere into a world where gravity begins to spin. For almost half a century after Einstein wrote his equations, physicists wondered whether a rotating black hole could even exist. Could space itself twist and whirl the way a storm does, dragging time into its motion? Or would the equations simply break apart, unable to hold such movement together? In 1963, an unassuming mathematician from New Zealand named Roy Kerr found the answer. Working alone in a quiet corner of Cambridge, he discovered a new exact solution to Einstein's field equations, one that described a rotating mass. It was the first of its kind, and it changed the story forever. To grasp what Kerr found, we need to imagine what rotation does to spacetime. When an object spins, whether it's a planet, a coin, or a star, it carries not only its mass but also its angular momentum, the measure of how much it twists as it turns. In Einstein's world, that twist doesn't stay confined to the object itself. It spills outward, tugging at the fabric of space. Near a spinning body, space-time begins to rotate too. It's as if the universe can't resist joining the dance. If you could hover above a rotating black hole, you'd feel that twist even from afar. Space would not be still beneath you. It would swirl, slowly at first, then faster as you approach the centre. The effect is called frame dragging, but we can think of it more simply. The rotation of the black hole drags space-time around with it, like a great spoon stirring the cosmic sea. To picture this gently, imagine a leaf floating on the surface of a whirlpool. The water beneath it spins, pulling the leaf into its flow. The closer the leaf gets to the centre, the faster it spins, until eventually it can no longer stay still. Near a rotating black hole, the same thing happens, but instead of water, it's space itself that swirls, and instead of leaves, it's light. Around every spinning black hole lies a region called the ergosphere, a zone where space rotates faster than any object can resist. You can't stand still there, not even in theory. The word ergosphere comes from the Greek ergon, meaning work, and indeed this region is full of potential energy. If a particle were to fall into it and split, part of it could be flung back outward with more energy than it had before, stealing a tiny fraction of the black hole's spin. It sounds almost mischievous, a way for the universe to take back a little of what gravity has claimed. Physicists call this the Penrose process, after Roger Penrose, who first described it in 1969. In everyday language, it means that a spinning black hole isn't a perfect prison. It leaks, ever so slightly, through the dance of its own rotation. But even before those discoveries, Kerr's solution revealed something remarkable. The singularity at the heart of a rotating black hole, the place where the old equation said everything collapsed into a point, wasn't a point at all. In his version, the collapse took the shape of a ring. This ring singularity is a circle of infinite density, spinning at the speed of light, stretched so tightly that space around it folds into strange, looping corridors. If we describe it softly, we might say, at the centre of a spinning black hole lies not a dot but a whirl, a loop of light so dense that space itself must dance around it. The mathematics behind this idea are notoriously complex, filled with twisting terms that describe how space and time trade places inside the horizon. But what they mean can be translated into a simple image. Imagine a funnel, like the one we pictured before for a Schwarzschild black hole. Now set that funnel spinning so fast that it begins to flatten at the bottom. The walls warp, the centre stretches, and suddenly, instead of a single pit, you have a circular opening, a ring where the geometry turns inside out. Through that ring, the equations suggest it might be possible, in principle, to pass into another region of space-time. On one side lies our familiar universe, on the other, something new. It could be another universe, or another part of this one, reached through a kind of hidden corridor. The Kerr black hole, in its pure mathematical form, contains not one but multiple layers of reality. An outer region where we live, an inner region beyond the first horizon, and deeper still, a doorway through the ring into the unknown. It's a vision both elegant and unsettling. The black hole is no longer a simple well of darkness. It's a structure, layered, dynamic, filled with motion. The outer horizon marks the point of no return just as before, but inside another boundary appears, an inner horizon, a zone where gravity's pull and the twisting of space balance each other for a fleeting moment. Beyond that lies the ring itself, spinning endlessly at light speed, shaping a tunnel of possibilities that may lead elsewhere. To the mathematician's eye, this was beauty made visible, a structure of pure symmetry and motion, carved from the fabric of the cosmos. But to physicists, it was something stranger, a hint that Einstein's equations, when set spinning, became not only more intricate but also more forgiving. In theory, nothing prevented a traveller from entering a rotating black hole and emerging in another region of space-time. The journey might pass through the ring singularity itself, a place where down and up, inside and outside lose their meaning entirely. Of course, reality is less generous than mathematics. Any real black hole, surrounded by dust, plasma and magnetic fields, would almost certainly destroy whatever approached its centre. But that hasn't stopped generations of scientists and dreamers from wondering what those equations were trying to tell us. Could rotation truly twist space enough to open a path? Or was this, like the Einstein-Rosen bridge before it, another mirage? An echo of what might be, but never is? For now, we can think of Kerr's discovery as the moment the universe began to whirl in our imagination. The black hole was no longer static or still. It became alive with motion, with eddies of time and loops of possibility. Even its shadow, the dark circle we might one day photograph, would be different because of that spin, flattened and brightened along one edge, like a halo seen from an angle. There's a quiet irony here. Einstein himself doubted that black holes could exist at all, yet his equations, in Kerr's hands, gave birth to their most realistic form. Every real black hole we've since observed, from the one in the heart of our galaxy to the giants at the centres of distant galaxies, spins. Some turn slowly, others almost at the speed of light, and in that rotation they carry the story of every star that ever fell into them, every fragment of matter that once circled their edge. So when you look at those images of black holes, those faint rings of light surrounding a darkness deeper than night, remember that inside them, space is not silent. It's turning, twisting, and dragging time along with it. Like a whirlpool without water, or a storm without wind, a spinning black hole is pure motion given shape. And from this motion, new questions arise. If rotation can reshape space-time, what happens deep inside, beyond the second horizon? Could those hidden corridors truly lead somewhere? Perhaps even to another universe? Or does the spinning geometry, beautiful though it is, fold in on itself once more, collapsing under the weight of its own light? Our journey now turns toward that question, toward the inner horizon and the door it may conceal, a door that glows faintly in the mathematics but remains closed in the stars. If we follow the thread a little deeper, the still geometry of Schwarzschild's black hole now feels far behind us. Here, in the spinning world of Kerr's solution, space and time don't just curve, they dance. Every point twists with the rhythm of rotation, and every direction becomes uncertain. Even the notion of a single boundary, a single event horizon separating what can escape from what cannot, dissolves into something more layered and strange. A rotating black hole doesn't have one horizon, it has two. The outer horizon is what we already know, the familiar surface of no return. To an outside observer, it behaves much like the horizon of a non-spinning black hole. Once crossed, light can no longer find its way out, but just inside it, nested like the lining of a shell, lies another boundary, the inner horizon, a place where gravity's pull and the twisting of space reach a kind of temporary balance. Between them lies a region unlike any other in the universe, the ergosphere, the whirlpool zone where space is dragged faster than any object can resist. To understand how these layers work together, imagine standing near a giant whirlpool in the ocean. At first, the water moves slowly and you can still paddle away. Closer to the centre, the current tightens and spins, carrying you helplessly around. Then, suddenly, there's a moment where the pull downward and the rotation sideways feel equal. The eye of the storm, not calm but momentarily balanced. That fleeting circle is like the inner horizon, a place where the rules of motion rearrange themselves before giving way to something even stranger below. Inside that horizon lies the ring singularity, the hidden door in Kerr's geometry. Unlike Schwarzschild's central point, this singularity isn't a dot but a loop, a circular knot of infinite density spinning at the speed of light. The space around it is so warped that the ordinary meanings of inside and outside break down completely. Paths through space-time, the trajectories that matter and light must follow, wrap around the ring in ways that seem impossible, yet are perfectly allowed by Einstein's equations. If we describe it softly, it goes something like this. At the heart of a spinning black hole, space bends so completely that falling no longer leads downward but around, and what was once an end becomes a corridor. Some paths around the ring curve back outward, suggesting, at least mathematically, that there might be routes leading from one universe to another, or from one region of space-time to its mirror image. On a Penrose diagram, these routes appear as delicate threads crossing from one triangular region to another, hints of other worlds just beyond the singularity. To see it with the mind's eye, picture a sphere drawn inward, spinning faster and faster until its poles flatten into a disk. At the centre of that disk, a hole appears, not a void, but a twist, like a whirlpool's throat. The geometry doesn't simply end there, it continues, folding back into another space, a kind of mathematical reflection where the arrows of time and gravity might reverse. In theory, one could enter this inner region and emerge into another universe entirely. The idea is so bold that it almost feels like fiction, and yet it lives inside the mathematics with quiet precision. The equations make no distinction between what we call our universe and what might lie beyond. They simply describe geometry wherever it goes. To the mathematics, moving through a singularity is no different than crossing a hilltop. Though for anything made of matter, the journey would be impossible. Reality, of course, is less forgiving. The same equations that permit these hidden doors also predict their downfall. The inner horizon, where the balance of forces briefly holds, is unstable. Any small disturbance, even a single photon of light falling inward, would upset the equilibrium. Energy would build up wave upon wave until the region collapsed into chaos. The once smooth passage would twist into turbulence, and the inner horizon would crumble into a true singularity. If we were to soften that into words, we might say, too much light in one place, and even space itself gives way. It's as though the universe allows perfection only on paper. The hidden door exists in the equations, yes, but in the living cosmos it's sealed by its own brightness. The spin that creates it also destroys it, turning potential corridors into walls of radiant collapse. Still, the idea remains haunting. The notion that deep inside a rotating black hole there could be a region where the future opens outward instead of inward, where falling might become rising, is one of the most poetic results ever to emerge from pure mathematics. It paints a picture of the cosmos as something endlessly recursive, folding back on itself in ways we can barely imagine. Einstein once described space-time as the softest of fabrics, yet the most unyielding of all realities. The Kerr black hole shows us what happens when that fabric is twisted beyond comprehension. Its structure is layered like a dream, outer horizon, inner horizon, ring, and beyond. Each layer adds a new rule, a new way for time and motion to behave. Outside, space flows like a river into darkness. Between the horizons, it swirls like a storm. Inside, it folds back like a reflection seen in rippling water. To stand at the edge of this geometry, even in thought, is to glimpse a world where direction, distance, and even causality become fluid. It's a realm that blurs the difference between falling and flying, between an ending and a beginning. On the Penrose map, the Kerr black hole looks almost like a pair of hourglasses facing one another, joined at the narrow waist of the ring. The outer regions stretch upward and downward, our universe above, another below, while the ring sits at the meeting point, the place where the flow of time might reverse. To one observer, everything falls inward. To another, everything bursts outward. Both stories fit depending on which side of the diagram you stand. And perhaps that's what the hidden door truly represents. Not a physical tunnel through which matter could pass, but a mirror of perspective. The universe might not allow us to cross from one side to the other, yet the geometry whispers that such symmetry exists. It's as if nature were telling us, you can imagine it, you can draw it, but you cannot live inside it. There's something deeply human in that limitation. We're always drawn to the threshold, to the idea that beyond the horizon, there might be more. In Einstein's spinning cosmos, the threshold is there, gleaming faintly inside the mathematics, unreachable but real. The two horizons, the ring, the hidden door, they form a kind of cosmic cathedral, a structure so precise and self-contained that it feels less like a discovery and more like something the universe always knew. And yet, as perfect as it seems, this spinning cathedral hides a flaw at its core. The balance is delicate, the structure unstable. Too much energy, too much motion, and the harmony collapses. The door closes on itself. What looked like a passage becomes a paradox. What looked like forever becomes a boundary. As we drift further into the story, that collapse will take center stage. The elegant corridors of Kerr's geometry, infinite in theory, begin to fall inward under their own weight. Infinity itself folds back, and the promise of endless universes becomes a single truth whispered softly by the cosmos. Beauty may be infinite, but reality always has limits. If we follow the thread still further inward, we arrive at the place where the mathematics of beauty begins to tremble under its own perfection, the point where infinite elegance collides with the limits of what nature can bear. The Kerr black hole, in all its spinning symmetry, seems at first like a miracle of balance. It unites gravity, motion, and time into a single seamless shape. And yet, when we peer too closely, the geometry begins to shimmer, not with mystery, but with warning. Inside the spinning black hole, beyond the first horizon and past the swirl of the ergosphere, lies a region where the very flow of cause and effect begins to unravel. In the pure equations, this inner space unfolds into a strange recursive network, a chain of worlds linked together by the ring singularity at the center. If we were to draw it as a diagram, it would look like an endless hallway of mirrors, each black hole leading into another universe, each universe containing another black hole, and so on, forever. The mathematics permits it. In fact, it demands it. For every path that falls through the ring, there is another that emerges elsewhere. The geometry doesn't stop. It repeats, like a melody echoing down an infinite corridor. But this infinity is fragile, an ideal that reality cannot maintain. If we describe it gently, we might say, the equations see forever, but the universe gets tired sooner. And this is where physics reasserts itself. The very rotation that makes Kerr's structure so intricate also makes it unstable. Every particle, every ray of light that falls into the black hole carries with it a trace of energy, a whisper of information that disturbs the perfect balance inside. Those disturbances don't fade, they grow. They pile up at the inner horizon, amplifying one another in an unstoppable cascade. In the language of mathematics, this is called an instability, but we can imagine it more simply, like echoes bouncing endlessly inside a hollow chamber. Each echo stirs the next, each vibration strengthens the one after it, until the sound becomes a roar and the walls themselves begin to shake. Inside the spinning black hole, that roar is made of light. Photons swirl, trapped in the loop of spacetime's spiral, their energy multiplying until even the smoothness of geometry can no longer hold. When that happens, the elegant corridors of Kerr's interior collapse into chaos. The delicate layers, outer horizon, inner horizon, ring, crumble under the weight of their own brightness. What was once a portal between universes becomes a storm of pure curvature. Time and space no longer trade places gracefully. They twist into a tangle where the very idea of sequence loses meaning. Physicists sometimes call this violent transformation the mass inflation singularity. It's a dry term, but what it means is simple. Too much energy in one place makes even space itself implode. The inner horizon, once thought to be a gateway, becomes a wall of fire, and the ring, once thought to be a doorway, becomes a knot so tight that no line can pass through. You can think of it as a kind of cosmic self-defense. The universe, sensing that its own geometry is stretched too far, folds back on itself to restore order. It's as if space-time says, no further. The perfect symmetry remains in the equations, a quiet ideal, untouchable, but in the real cosmos the structure collapses into something simpler, humbler, finite. Yet even as the dream of endless universes fades, it leaves behind something profound. The Kerr solution, even with its flaws, shows us that space and time are capable of far greater contortions than we once imagined. It reveals that rotation, motion, and energy can warp the very shape of reality, not just bending it, but twisting it into loops and reflections. It suggests that, at the deepest level, the universe is not linear at all, but recursive, always folding, always reshaping itself, and perhaps, in a quiet way, that's enough. The infinite chain of black holes and white holes might never exist in the heavens, but they live within the mathematics as symbols of possibility. They remind us that symmetry is not a promise, it's a language. The equations whisper of perfection, but the cosmos answers with compromise, and in that compromise reality finds its balance. Einstein's theory allows such dreams because it is built on reciprocity. Space tells matter how to move, and matter tells space how to curve. But once matter becomes too dense, too bright, too complex, the conversation falters. The smooth dialogue turns into noise, and when that happens, the universe seems to choose silence. A new singularity, an endpoint, a place where questions can't pass through. If you imagine standing near the edge of such a black hole, it might help to think of it as a great whirlpool whose centre is hidden in mist. From afar the water seems calm. Closer in, it begins to spin, drawing everything into its flow. And deep below, where the current becomes impossibly fast, the whirlpool folds back on itself. The surface closes, smooth again, as though the opening had never been there. What remains is motion, unseen, eternal, contained. The Kerr black hole, then, is both a revelation and a caution. It shows us what happens when the universe pushes its own equations to their limits. It reveals that even infinity has structure, that eternity can be mapped, if only briefly, before it collapses back into stillness. And it reminds us that beauty, in physics as in life, often lies at the edge of what can survive. If we were to describe the lesson softly, it might be this: even infinity must pause for breath. In that pause lies everything, the balance between what the mind can imagine and what the cosmos will allow. For every impossible doorway that mathematics opens, the universe offers a quieter truth, that there is grace in limits, peace in boundaries, and wonder even in endings. Perhaps that's why physicists, even knowing the instability, still find the Kerr geometry beautiful. It represents a kind of yearning, the desire for connection, for continuation, for the idea that no fall must end. And even though nature forbids the endless chain, the equations keep it alive like a melody that lingers after the song has ended. So when we think of the black hole's heart, of that spinning ring surrounded by two horizons and wrapped in layers of light, we might imagine it as both infinite and finite at once. A dream the universe had, but could not quite keep. And as we step back from this vision of swirling infinities, we find ourselves at a turning point in the story. The equations have given us every gift they can, from horizons and bridges to spinning doors and collapsing light. What comes next is not expansion, but reflection. The universe begins to close its open hands, showing us how it protects its balance. From here, our journey turns outward once more, to the greater lessons hidden in these collapses and constraints. For even as black holes guard their secrets, the cosmos keeps whispering the same promise, that beauty never truly disappears. It simply folds itself into a quieter form, waiting to be seen again. The path now carries us into the quiet spaces between things, the thin, humming emptiness we call the vacuum. From a distance, it looks like nothing at all. But as Einstein and the physicists who followed him discovered, nothing is not really empty. It's a restless ocean of potential, where tiny fluctuations appear and vanish, like bubbles rising and popping in invisible water. For a moment, a pair of particles might flicker into existence, borrow a little energy from nowhere, and then disappear again before the universe can notice the debt. It's in this peculiar landscape, half dream, half law, that physicists tried to find a way to make Einstein's bridges last. If the original Einstein-Rosen bridge collapsed too quickly to cross, perhaps there was some way to hold the throat open, to balance the tug of gravity with something equally strong but opposite, a push rather than a pull. In 1988, two American physicists, Kip Thorne and Michael Morris, set out to see if the universe might allow such a thing. They weren't searching for science fiction, they were simply following the equations wherever they might lead. What they found was both tantalizing and humbling. Yes, the equations did allow a bridge that stayed open. A traversable wormhole, but only if the tunnel was threaded with something very peculiar, negative energy. At first this sounds harmless enough, like a mathematical curiosity. But negative energy is not just less than zero, it's the kind of thing nature resists entirely. We're used to thinking of gravity as a pull, masses attracting, curving space inward. Negative energy would be the opposite, a push, a kind of gravitational repulsion. It would stretch space instead of squeezing it. You could think of it as the universe's equivalent of asking someone to inhale and exhale at the same time. It's possible on paper, but exhausting in practice. In soft terms, it's like asking the cosmos to lie. The equations might permit it, but reality only pretends for a moment before returning to honesty. Morris and Thorne calculated that to keep a wormhole's throat open, you'd need enough negative energy to counterbalance the inward pull of gravity everywhere along the tunnel. The tiniest lapse, and the bridge would collapse in an instant. It was like holding the mouth of a straw open underwater while the ocean tried to crush it shut. You could do it briefly, with tremendous precision, but not for long. Quantum physics, however, gave them a glimmer of hope, because the vacuum itself, that restless ocean of near-nothingness, sometimes produces regions of negative energy, tiny, fleeting patches where the quantum fluctuations tilt slightly below zero before bouncing back. One real-world example of this is known as the Casimir effect, named after the Dutch physicist Hendrik Casimir. Imagine placing two metal plates very close together in a vacuum, so close that only certain wavelengths of light can fit between them. Outside the plates, all wavelengths can exist freely, but inside only a few do. That imbalance creates a gentle pressure, as if the space between the plates contains less energy than the space around them. In that narrow gap, the universe has, in a sense, gone into debt. It's a small, quiet act of negative energy. If you could magnify that effect to a cosmic scale, you might be able to build a wormhole that stays open. The bridge would be held apart not by matter, but by the vacuum's own borrowed breath. A thin shell of negative energy preventing gravity from closing the tunnel. But the universe is strict about its loans. It allows you to borrow from the vacuum, but only for a moment, and only under impossible precision. This rule is sometimes written as a quantum inequality, but we can express it more gently. You may take from nothing, but only if you give it back before time itself can blink. It's a kind of cosmic accounting that keeps the universe honest. You can hold your breath underwater for a few seconds, but not for a journey across the ocean. The same applies here. The negative energy that could keep a wormhole open is fleeting, the physical equivalent of a sigh. Before any traveller could pass through, the vacuum would reclaim its loan and the tunnel would collapse. Even if one could somehow gather enough of that exotic matter, the act of placing it would likely destroy the geometry you were trying to sustain. The energy fluctuations near a wormhole's mouth would grow chaotic, heating the tunnel and distorting spacetime until the structure gave way. It's as though the bridge, feeling the strain of its own contradiction, quietly erased itself. When Morris and Thorne finished their calculations, they realised something bittersweet. The dream of a traversable wormhole, a bridge not just in math but in reality, wasn't forbidden, but it was profoundly impractical. Nature, it seemed, allowed the idea but refused the implementation. And yet there's a strange beauty in that refusal. It's not a harsh no, but a whisper. You may imagine it, but not build it. The universe keeps its symmetry intact in theory, but guards its stability in practice. You might say it allows the dream for the sake of poetry, even as it forbids the experiment. In a way, that's what makes the cosmos so graceful. It lets us see what might be possible, just enough to glimpse perfection, and then quietly reasserts its limits. The negative energy that would sustain a wormhole flickers in and out of existence all around us, reminding us that even emptiness is alive with potential. The vacuum hums, the quantum fields ripple, and for tiny intervals of time, the impossible becomes almost real. Physicists sometimes joke that the universe runs on credit, that every particle in existence is a loan from nothing, paid back through the balance of creation and annihilation. But even in that grand economy, there's no infinite overdraft. The cosmos knows its limits, and those limits are what keep it whole. So the traversable wormhole, the dream of walking through space to another star, another universe, or even another moment in time, remains for now a creature of equations and imagination. The math says, yes, but only briefly. Nature replies, not yet, and perhaps never. But that tension between yes and no, between possibility and restraint, is part of the universe's quiet genius. It ensures that reality never unravels under the weight of its own creativity. The cosmos may play with negative energy, but it always settles its debts. It may hint at shortcuts, but it never lets them stay open long enough to break the flow of causality. And perhaps that's for the best. If the universe were filled with open wormholes, if every distance could be crossed instantly, if every separation could be undone, then time itself would lose its meaning. There would be no before or after, no here or there, just a blur of everything at once. What keeps the cosmos peaceful is not its infinite possibilities, but its gentle refusals. As we drift onward, we'll see that this pattern repeats everywhere, that for every door mathematics opens, the universe quietly closes it with care. It's not punishment, it's balance. The next part of our journey will show us just how far that protection goes, how space-time itself guards its secrets, locking away every shortcut, every tunnel, every hidden passage until only the honest paths remain. If we keep listening to where the equations whisper next, we find that the universe, like any careful storyteller, guards its secrets with quiet precision. It does not allow chaos to spill into its plot lines. It writes its laws in such a way that the story of cause and effect remains unbroken, every chapter following from the last. For centuries, human imagination has searched for shortcuts through this narrative, hidden tunnels, secret passages, back doors through time, but nature, ever patient, always closes them. The dream of the traversable wormhole was one such passage, a breathtaking possibility where space could fold in on itself, connecting two distant points with a single curve. Yet, as we saw before, those tunnels collapse before anyone can cross them. Still, the question lingered. Could there be another way? Could a universe as vast and mysterious as ours really have no hidden hallways at all? Physicists, ever hopeful, tried to test the limits. They explored the equations again and again, pushing at the edges, trying to find loopholes where the rules might bend. But the universe, it turns out, is more consistent than cunning. Even in the wildest corners of Einstein's mathematics, a quiet principle stands guard, one that ensures that space, time, and causality cannot be tricked. This principle is known as topological censorship, though the name sounds harsher than the truth it holds. What it means, in gentle language, is that the universe hides any usable shortcut. The cosmic fabric may twist and fold, but it never lets those folds stay open long enough for travellers to slip through. The pathways may exist in theory, but in reality they are sealed, their entrances disguised, their exits erased. You might imagine it like this. The universe is a grand house, ancient and intricate, filled with endless rooms. Here and there the walls curve oddly, suggesting secret passages behind them. And every so often someone discovers a door, faintly outlined, almost real, leading who knows where. But when they reach out to open it, the handle vanishes. The wall smooths itself over. The house keeps its secrets. Topological censorship was proved in the 1990s, but its essence was already written into Einstein's geometry. It arises from something very simple, the honesty of matter. In our universe, energy behaves responsibly. It adds when it should add, subtracts when it should subtract. It follows rules of positivity that ensure no region of space-time can be twisted too far without consequence. If the equations are asked to create a wormhole wide enough for a signal to pass through, those same energy conditions push back, forcing the geometry to collapse. If we translate that principle into softer terms, we might say, the universe protects causality the way a body protects its heartbeat. It's not an act of cruelty, but of preservation. Allowing shortcuts would break the rhythm of cause and effect, the pulse that keeps reality coherent. If one event could influence another faster than light, or if information could emerge from nowhere, time itself would lose direction. The universe's story would splinter into paradoxes, so it builds its own immune system, ensuring that no tunnel, no wormhole, no hidden passage can survive long enough to disrupt its flow. Even the mathematics of space-time seems to conspire in this protection. The moment a geometry begins to open a shortcut, the energy it would require starts to diverge. The walls of the tunnel would heat up, its structure would shake, and the surrounding space would bend until the passage closed itself. It's as if the cosmos responds to every attempt with a soft but firm no. And yet, there's kindness in this refusal. The universe doesn't erase beauty, it simply keeps it private. The elegant structures we find in Einstein's equations, wormholes, white holes, spinning corridors, bridges between worlds, are not mistakes. They are glimpses of what perfect symmetry would look like if perfection could survive. But nature, knowing that perfection cannot hold, keeps those patterns folded safely inside its math, like pressed flowers between the pages of a book. If we could listen to the cosmos in this moment, perhaps it would whisper something like, "You may see my hidden corridors, but you may not walk them. And that too is a kind of grace. Because these restrictions, these locked doors, are the reason we can live inside a universe that makes sense. Without them, light could arrive before its source, effects could precede causes, and every thought or motion would collapse into confusion. The very fact that we can remember the past and imagine the future depends on the universe's refusal to let time turn inside out. It's a quiet form of mercy, really. The way space-time guards its structure, the way a mind guards its sanity. Every time we try to imagine a way around it, we find that the rules are stronger than our cleverness. The cosmic house stays orderly, its foundations hold. Still, physicists keep exploring the possibilities, not out of defiance but curiosity. Each time a new theory arises, quantum gravity, string theory, holographic space-time, the question returns. Might there be a loophole here? A tiny place where the walls bend enough to open a door? And each time, the universe answers with the same serene balance. The geometry adjusts, the energy conditions tighten, and the shortcut fades back into dream. But the beauty doesn't vanish. It simply becomes hidden. An inner architecture that reminds us of how much structure lies beneath what we see. Like the roots of a tree, invisible but essential, these forbidden shapes support the rest of reality. They're what keep the forest standing. It's tempting to feel disappointed by that. We humans are creatures of curiosity and reach. We long to cross every boundary to see what lies beyond. The idea that the universe hides its doorways can feel unfair, as though we're being kept from something wondrous. But perhaps this is the universe's way of teaching humility, showing us that some mysteries are meant to remain intact, not because we are unworthy, but because they are what hold everything else together. And so, the wormholes remain folded in the dark, the white holes remain unlit, and the hidden passages of space-time stay sealed. Not destroyed, just preserved, the way secrets sometimes are when silence protects their meaning better than words ever could. It's comforting in a way. The same laws that stop shortcuts also protect stars from collapse, atoms from disintegration, and life from unravelling. The universe locks its doors not to exclude us, but to keep the story coherent, to let it unfold page by page, moment by moment, in order. It gives us a cosmos we can trust, one that may be full of mystery, but never of betrayal. So as we drift onward, we carry this understanding. The cosmos is not cruel when it says no. It's kind. It preserves causality the way a heart preserves rhythm. It protects truth the way a horizon protects light, not by destroying it, but by shaping where it can go. And beyond those locked doors, there's still beauty. We may not pass through, but we can see the glow that seeps through the edges. In the next part of our journey, that glow will take form. The dreams we've followed through math, black holes, wormholes, horizons, will finally appear before our eyes, drawn in light, confirmed by sound, turning what once seemed like fantasy into quiet fact. From here, the story turns from equations to evidence, from the quiet imaginings of Einstein's chalkboard to the instruments of a century later that could finally see and hear what he had only dreamed. For decades, black holes were whispers in mathematics, elegant predictions drawn in invisible ink. They existed in theory, but not in sight. Scientists spoke of them cautiously, as though naming something that might not yet wish to exist. And then the universe answered. It began with a telescope that was not one telescope at all, but many. A ring of observatories scattered across the planet, each one listening to the same patch of sky at precisely the same moment. Together they formed a single, Earth-sized lens, sharp enough to see the unseeable. This global collaboration was called the Event Horizon Telescope, and in 2019, It gave humanity its first direct glimpse of a black hole. The object they captured was called M87 Star, a supermassive black hole at the centre of the giant galaxy Messier 87, 55 million light-years away. What the image revealed was hauntingly familiar to those who had studied Einstein's equations, a bright ring of light encircling a dark centre. The light came from matter heated to billions of degrees as it spiralled inward, and the darkness was not shadow, but silence, the event horizon itself, the place where light surrenders to gravity. For years that image had existed only in computer simulations and theoretical sketches, the product of patient math and imagination. And now there it was, not drawn, but observed, a golden halo glowing around a void. The scientist who worked on the project described the moment as surreal. After months of processing data, petabytes of radio waves gathered from across the Earth, the image slowly appeared. One of them said it felt like the universe had looked back at us. The structure matched precisely what general relativity predicted. The size of the shadow, the brightness of the ring, the way the light curved around the darkness, every detail agreed with Einstein's vision. It was proof not just of black holes, but of the extraordinary accuracy of the theory that predicted them. Einstein, who had doubted that nature would ever create such extremes, was now vindicated by a photograph taken a century after his equations. The cosmos had drawn his math in light. 2 years later, the same team turned their attention closer to home, to the heart of our own galaxy, where another supermassive black hole waits, quieter but no less magnificent. They called it Sagittarius, a star, a body 4 million times the mass of our Sun, hidden behind veils of dust and gas at the centre of the Milky Way. And again, the telescope saw what the equations had promised, a glowing ring surrounding a soft, dark core. Unlike the distant giant in M87, this black hole is restless, flickering with bursts of radiation as it consumes small pockets of matter drifting too near. But the shape, that perfect circular darkness, is the same. It is the universal signature of the event horizon. The stillness that exists not because nothing happens, but because nothing can be seen. If we translate that softly, it says, even darkness glows if you wait long enough. While the Event Horizon telescope was showing us black holes in light, another set of instruments was listening for them in sound, though not sound in air, but the tremors of spacetime itself. In 2015, the LIGO and Virgo collaborations made history by detecting the faintest ripples ever recorded, gravitational waves caused by 2 black holes colliding more than 1 billion light-years away. For the first time, we heard space-time ring like a bell. The waves stretched and compressed the Earth by a fraction of the width of a proton, and yet from that whisper, scientists could reconstruct the entire story. 2 massive stars orbiting faster and faster, spiralling inward until they merged into one. The final pulse of energy that escaped that collision was enough to shake the universe, yet it arrived here as a ripple smaller than an atom. Einstein had predicted these waves in 1916, the same year Schwarzschild discovered the first black hole solution, but he doubted anyone would ever detect them. 100 years later, they became not only detectable, but measurable, revealing the last moments of merging black holes in perfect detail. If you could listen to that cosmic event as music, it would rise in pitch as the 2 black holes approached each other, a long, slow hum climbing to a single, sharp note, and then silence. That sound is now known affectionately among scientists as a chirp, a tiny song sung by the fabric of the universe. When LIGO recorded the first one, the data lasted less than half a second, and yet in that instant, a prediction made in pencil was confirmed by the trembling of space-time itself. It was as though the universe had nodded quietly in agreement. Today, these detections continue. Gravitational wave observatories now listen constantly, hearing not only black holes but also neutron stars, cosmic collisions, and perhaps soon, the distant echoes of the Big Bang. Each signal is a reminder that Einstein's dream, that geometry could describe reality, was not fantasy, but foundation. What began as absurd mathematics, as many once called it, has become something we can see and hear. The black holes that were once theoretical ghosts now reveal themselves as the engines of galaxies, the keepers of cosmic rhythm. And the same equations that describe their edges also explain the expansion of the universe, the bending of light, and the ticking of time. It's remarkable how gently the universe reveals its truths. For nearly a century, the evidence was hidden, waiting until our technology, our patience, and our understanding could catch up. It's as if the cosmos wanted to make sure we were listening closely enough before it spoke. And yet, even as we marvel at these confirmations, some dreams remain untouched. White holes, wormholes, the bridges between universes, they still live only in the margins of mathematics, beautiful but unseen. The equations allow them, but nature keeps them hidden. Perhaps that too is part of the design. The universe lets us see just enough to keep wonder alive, a balance between revelation and mystery. For every question it answers, it leaves another gently unopened. So now, as we reach the quiet edge of our journey, we can rest in that balance. We have seen light bend, time stretch, and space itself ripple like water. We have watched equations become images and predictions become proof, and yet the mystery remains, humming softly beneath it all. In the next part of our journey, we'll step beyond the data into reflection. We'll ask what it means that so much beauty exists in theory and so much restraint in reality. We'll wonder whether impossibility, too, can be a kind of grace, a way for the cosmos to stay whole, coherent, and peaceful. For even in saying no, the universe somehow keeps its poetry. As we drift into the final part of our journey, the story begins to quiet again. The equations that once thundered with black holes and collapsing stars now lie open before us like pages at rest. Their symbols no longer demand calculation, they invite contemplation. For in the end, the story of general relativity isn't only about what the universe allows, but about what it chooses to make real. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. He meant that the same human mind that dreams in abstractions, numbers, geometry, symmetry, can describe the cosmos with such uncanny accuracy. The equations of general relativity were, in a way, a poem written in the language of curvature and time. And yet, for all their beauty, they didn't decide what was true. The universe did. We've seen this pattern throughout our exploration. The mathematics permits white holes, but nature prefers black ones. It allows wormholes that could join distant skies, but the cosmos seals them before they can be crossed. It offers infinities and mirror universes and corridors of light, yet the real universe, the one that hums above our heads, chooses restraint. It's almost as though mathematics is the imagination of reality, while physics is its memory. One dreams, the other decides. Think of the two as old friends walking together. Mathematics looks outward, seeing endless possibilities stretching into infinity. It sketches what could exist. Universes layered upon universes, symmetries upon symmetries, a perfection too flawless to endure. Physics, walking beside it, watches quietly and shakes its head. Beautiful, it says, but this one holds, this one breathes, this one works. There's a kind of wisdom in that partnership. The universe does not discard beauty, it curates it. It allows just enough of mathematics to manifest in matter, to make the world elegant, but not so much that it becomes impossible. It keeps a balance between the abstract and the actual, between what could exist and what must remain thought. Take black holes, for example. When Schwarzschild first wrote his solution in the mud-soaked trenches of World War I, many dismissed it as a mathematical curiosity, too extreme, too clean, too improbable. But a century later, we've seen them not only through telescopes but through ripples in space-time itself. Here, the universe said, yes. And then there are the white holes, the perfect time-reversed twins, equally allowed by the same equations. To them, nature said no, or perhaps more kindly, not in this world. The difference between the two is not logic, but preference, a choice embedded in the structure of reality. The laws are symmetric, but the universe breaks that symmetry in favour of something more sustainable, more stable, more real. In this way, impossibility becomes not a punishment, but a kind of protection. It keeps existence coherent. If everything the equations allowed were to appear, the cosmos would collapse under its own imagination. It would be too full, too tangled, too unstable. The locked doors of physics, the limits we've encountered, are what make the rest of the house livable. Perhaps this is why every great leap in science begins with something the universe once forbade. Black holes were once mathematical monsters. Gravitational waves were once undetectable whispers. The expanding universe itself was once a mistake in the equations. Yet each of these impossibilities became real when our understanding caught up. The line between dream and truth is thinner than we think, but it's not non-existent. Nature still decides where it's drawn. If we soften that idea into a single sentence, it might sound like this. Equations are invitations. Nature sends selective RSVPs. This balance between dreaming and deciding is what makes physics both humbling and human. We learn that not every no is a rejection. Sometimes it's the pause before a deeper yes. The universe seems to reveal itself gradually, as if testing our patience, ensuring that each truth is accepted not as spectacle, but as understanding. And in that patience, there's something profoundly gentle. Nature could have been chaotic, unpredictable, uninterpretable, but it isn't. It speaks in patterns, in laws, in shapes we can trace. It builds black holes that follow the rhythm of geometry. It sends waves that ring like music through space-time. Even its refusals are symmetrical, graceful, like the quiet gesture of a hand closing around light so that we can see the shape of its shadow. Mathematics dreams in absolutes. Perfect circles, infinite bridges, endless reflections. The universe builds with imperfection, or perhaps we should say, with tolerance. It allows error, entropy, decay, warmth. These are not flaws, but features. They make existence soft enough to hold, fragile enough to mean something. If the cosmos had granted every dream of mathematics, infinite wormholes, eternal motion, perfectly reversible time, it would be cold, timeless, lifeless. Nothing would change, nothing would end, and nothing would matter. By allowing some things to collapse, by letting others fade, the universe makes room for creation, for evolution, for us. In that sense, the laws of physics are acts of mercy disguised as constraints. Gravity limits how fast we can move, but it also binds us to our home. Entropy ensures that stars burn out, but it also allows them to shine in the first place. The speed of light may set a limit, but that limit keeps cause and effect in order, preserving the story of time. Perhaps impossibility is just another word for balance. It's easy to look at equations and wish for the beauty they promise, the infinite bridges, the perfect symmetries. But if you listen closely, there's beauty in the boundaries too. The fact that we can predict an eclipse, send a spacecraft across 1 billion kilometers, or measure a gravitational wave from galaxies away, that's the kind of perfection nature allows. It's not infinite, but it's enough. The physicist Subramanian Chandrasekhar once wrote that the universe is not only stranger than we imagine, it is stranger than we can imagine. Yet even in that strangeness, there's harmony. The equations reach outward, the universe answers inward, and between the two, everything we know comes to life. So, as we prepare to close this long journey, from horizons and bridges to spinning infinities and quiet refusals, we can rest in a simple truth. The cosmos doesn't choose between imagination and reality. It needs both, one to dream and one to decide. And in that balance, it becomes something more than either, something living, evolving, endlessly unfolding. A universe where limits create meaning, where silence shapes sound, and where every impossibility hides a deeper invitation to wonder. Our quiet exploration now turns toward reflection, toward the closing of the circle we began hours ago, when we stood at the edge of Einstein's equations and wondered what would happen if we simply followed where they led. We've seen black holes swallow light, white holes shine only in theory, wormholes collapse before a single traveller could pass, and space-time itself ripple like a great cosmic lake. Now, in the stillness at the end of all that motion, a gentle question remains. If mathematics allows so many universes, why does nature seem content with just one? The British physicist Geraint Lewis once put it simply, "We have one universe, why not two?" It sounds almost playful, but hidden inside that question is the bittersweet humility that comes when curiosity meets reality. Mathematics, after all, gives us permission to imagine infinite worlds. Equations do not stop at one horizon. They repeat, mirror, and multiply, describing versions of space-time that might exist beyond our reach. In theory, the fabric of reality could be woven into countless separate tapestries, each with its own laws, its own stars, its own arrow of time. And yet, here we are, in one. It's easy to think of that as limitation, but perhaps it's something else, a kind of peace, a single universe, unfolding with care, obeying its own rhythm. One where light travels just fast enough for us to see the stars as they once were, where time moves forward so that stories can have beginnings and endings. If there were many, we might lose the intimacy of the one we have, the gentle order that makes it possible to remember yesterday, to dream about tomorrow, and to exist in the small miraculous now. To understand how special that is, let's return just for a moment to the image where we began, the thought experiment of a rocket hovering above a black hole. We imagined an astronaut steady in the void looking down toward the event horizon. From her point of view, everything near that edge seemed to slow and freeze, the clock hands of the universe pausing in a kind of suspended breath. But now, after everything we've learned, we can see that the frozen image was only half the truth. The astronaut wasn't watching time stop, she was watching it stretch, a single thread of reality drawn so long that it seemed motionless. On the other side of that horizon, time continued. Not in defiance, but in completion. The story didn't end. It simply turned the page somewhere she could no longer see. That's what the universe seems to do at every limit. Continue quietly beyond our perspective. Whether it's the hidden core of a black hole or the invisible edge of the cosmos itself, there's always another side. Not necessarily another universe, but another way the same one goes on. It's a continuity that feels both infinite and intimate, as though the cosmos prefers to stay whole rather than multiply itself. We can think of it this way. Every mathematical possibility is like a reflection on a lake at night. The stars above shimmer across the surface, creating hundreds of perfect copies, but only one set is real, the ones that burn. The rest are gentle illusions existing to remind us how deep the water is and how still it must be to mirror so much. That is what mathematics offers. Reflection. What physics offers is the light itself. When Einstein followed his own equations, he never imagined how far they would take us. To the edge of time, through collapsing stars, into regions where gravity becomes geometry, and space itself falls faster than light. He didn't expect that the math, so clean on paper, would one day be photographed in the glow of a distant galaxy. Nor could he have guessed that 100 years later, His ideas would let us hear the universe, the soft chirp of merging black holes echoing across billions of years. He gave us a tool for imagining perfection, and the universe gave us the beauty of imperfection instead. A reality slightly less symmetric, slightly more alive. And perhaps that's the reason we have one universe and not two. Because a single, coherent story can contain more wonder than an infinite library of unread pages. If you look up tonight, somewhere between the constellations, you'll see the faint blur of the Milky Way, a river of stars curving softly across the sky. It's easy to forget that we're inside that river, drifting with it. Every atom in your body, every photon that touches your eyes, once belonged to that same cosmic current. You are part of the same geometry Einstein tried to describe, the same curved fabric that folds time and space into being. You don't need another universe to find mystery. You're living inside one already. And maybe that's the quiet gift of following Einstein's math, realizing that the strange and the sacred are not separate. The very equations that describe a black hole's darkness also describe the pull that keeps you standing on the Earth. The same curvature that traps light also guides the moon across the sky. The same fabric that collapses stars is the one that cradles your every breath. It's all one story, told at different scales, sung at different pitches. From galaxies spiraling in slow, luminous arcs to neurons flickering in your mind as you try to picture them, it's the same song, carried across time and matter. If we were to translate the meaning of this long journey into one final whisper, it might sound like this. Every ending is just a change in perspective. The stars we see tonight are already gone. Their light travelling millions of years to reach us. And yet, that light still touches your eyes, still paints the night with their memory. In that sense, nothing ever truly ends. It simply moves beyond the part of the universe we can see, still existing, still unfolding, somewhere just out of reach. So as we close our exploration, take one last slow breath. Let the day fade, and let the quiet hum of the cosmos fill the space around you. You are here, in a universe that dreamed itself into being and allowed you for a fleeting moment to wonder why. If your thoughts are still drifting among those curved lines of space-time, let them drift. The universe is still humming, softly, all around you. And so we've reached the end of tonight's journey, a circle that began with curiosity and ends with calm. Thank you for travelling through it with me. If your eyes are growing heavy, that's all right. The stars will keep watch, the math will keep dreaming, and the universe, our single, exquisite universe, will keep on deciding.